Okay.
Sure.
Okay. Testing. Okay, great. Okay, welcome everyone to the Mars Geochemistry, the Fellowship of the Elements session. We've got a great set of presentations today from orbital to in situ, covering igneous, sedimentary, metamorphic processes across Mars and Mars analog sites. I'm Christina Viviano. I'm from Johns Hopkins University Applied Physics Lab, and I'd like to introduce my co-chair, Rachel Slank, and from LPI, and our moderator, Audrey Putnam from Rice. And so welcome everyone, and please enjoy the session.
Oh, I didn't open it. No, she's gonna let you read the time. Okay. So just as a reminder, we're already in Thursday, but you have 10 minutes to give your talk. We're gonna raise our hand at 2 minutes. At 10 minutes, we are gonna have to cut you off just to keep everything in time. Once we have our talks with 4 people, we'll do the 20-minute Q&A. So save your questions and then happily go to the mic. Also, as a reminder, if anyone would like to judge Dwarniks, we are in desperate need of some poster Dwarniks for tonight. So if you are interested, you can come up to the table and we can give you that information.
Awesome. And if speakers can get mic'd up over there beforehand, everybody please silence your phones. And for questions, use the mics at the front of the room and identify yourself with your name and affiliation. And all discussions and questions, of course, should focus on the science and be professional.
Okay, and for those of us joining us online, please submit your questions using the Zoom Q&A and ID yourself with your name and affiliation for all of us in person. The Zoom webinar Q&A will be used, and Slack can be used for after this to continue all those discussions that you want to keep on having. And these sessions will be recorded and they'll be available for 30 days after the conference.
And then also as a last reminder, the LPSC ambassadors are going to be posting online highlights. If you do not want your talk to have pictures taken or posted online, please say so, like as soon as we introduce your name. Again, just a reminder, photography and streaming of the presentations is not allowed, so please don't do that. We have 2 minutes, so we'll get started in about 2 minutes.
I'm not sure if we said that, but for speakers, you've got your time in front of you. A yellow light will pop up with a 2-minute warning. We'll also hold up 2 fingers, and it looks like you're not wrapping up. We'll tell you when you have 30 seconds.
You can minimize delay.
All right, so we're going to start the session off with my co-chair, Christiana Viviano, and she will be talking about the alteration of pre-Noachian Mars. So take it away.
Okay, thanks so much. Let's see. There we go. So today we are talking about the most ancient periods of Mars. And why do we care about them? Well, on ancient Earth, our best evidence for life dates back to the Archean, but there are potential signs that extend back into the Hadean period or era. And so these forms of evidence come through inclusions of graphite within zircons that have biogenic carbon isotopic signatures. And this suggests that life potentially originated on Earth when Earth was still in a stagnant lid regime in the Hadean era, and before plate tectonics had begun. And why this matters is that Mars is also in a stagnant lid regime, and it suggests that it's maybe compatible then with, in its earliest period of habitable conditions, and potentially a place where life could have taken hold. And Mars's surface preserves much more of the ancient rock record than Earth's. So like less than 6 grams of the zircons from the Hadean, versus you can see Mars, the cumulative fraction of surface area that's exposed from what's comparable to Archean and even the Hadean show up on Mars much more abundantly. And what also is interesting is that if, while it's still contested exactly when the Martian core dynamo existed, if it was available prior to the formation of these large impact basins, that would have protected surface habitability. And so this is all motivation then to investigate the oldest or pre-Noachian rocks on Mars. And where do these pre-Noachian rocks occur? Well, the start of the Noachian period is dated by the Hellas impact basin. So by definition, anything that Hellas, has busted into and uplifted surrounding that basin in the form of massifs is exposing and sampling pre-Noachian lithologies. And these are best exposed along the northern rim of Hellas, where ice is less stable in Martian winter, and thus the surfaces have been less reworked. And so my co-author, Michael Phillips, led a study in 2022 showing that along the northern rim, there's these beautiful exposures of plagioclase-dominated lithologies in CRISM multispectral mapping data that have been confirmed in targeted spectra, as well as analyzed with THEMIS data to show that it's consistent with an anorthosite-like composition that's widespread throughout this region in the yellow dots. And further work we've done have shown that similar CRISM mapping through the northern rim and then into Terrena Terra to the north in Noachian age terrain shows a transition in primary lithologies that basically goes from the pre-Noachian, where we're seeing this plagioclase signature, into the Noachian, where it disappears. And it's more dominated by olivine and low calcium pyroxene with an increasing HCP signal into the late Noachian. And interestingly, we also found that in these pre-Noachian exposures, the prevalence of alteration was about 3 times as much as in the Noachian period. So today I'm going to talk about results from CRISM targeted observations throughout the northern rim of Hellas into the Terrena Terra region, which is Noachian aged, and surrounding the Isidis impact basin. And these are, thousands of outcrops that we've identified the mineralogy. And the emphasis of this work is on the detailed mineralogy that you can get from the hyperspectral targeted data, despite the fact that obviously the sampling is much less uniform than you get with the mapping mode data. And so I'm going to walk through the mineralogy that we've observed in the targeted observations through time. The upper pie charts represent the primary lithologies that we've identified, and the lower pie charts represent the alteration mineralogies that we've identified in these terrains. And so I'll start with the pre-Noachian age material, or the material in the early Noachian Highland Massif unit. And This, I'm highlighting here with the arrows how they differs from the other periods. So in the pre-Noachian, we have an enhanced plagioclase signature and an enhanced MgOH phase, which is a dehydrated phase and very different from a magnesium smectite signal that we see all throughout the pre-Noachian and into the Noachian. That's shown in the dark green color, so I won't really reference it because it's pretty comparable between the ages. Into the early Noachian, we get an enhancement in low calcium pyroxene, and the alteration is dominantly prehnite, chlorite, zeolite. And all of these alteration phases form at elevated temperatures and sort of hydrothermal settings. And so this is telling us something about the alteration during the early Noachian period. As we move into the mid-Noachian, we sample the material that's surrounding Isidis. And so we see a big enhancement in the olivine signature, which is corresponding to the olivine carbonate unit that surrounds Isidis basin. And of course, we see a parallel with the carbonate signature as well, mostly in that the unit that surrounds Isidis, but also some carbonate in the rest of the mid-Noachian terrains. And then lastly, we have the late Noachian, which we have less sampled, so I won't really harp on that here, but it's pretty comparable to other Noachian aged units. So the take home here is that the pre-Noachian, in the pre-Noachian, the primary signatures are uniquely dominated by plagioclase, and the alteration signature is uniquely dominated by this MgOH phase, which I won't show here, but we've shown to be comparable to talc. And so this is sort of what it looks like if you zoom into one of these massifs along the northern rim and you map in the mineralogy from Chrism, you can see that there's a distinct spatial association between many of these, but this is kind of like our highlight one, of the feldspathic and orthositic, plagioclase bearing lithology shown in kind of white here, and a surrounding talc or MgOH phase shown in cyan. And we see this commonality, and sometimes we even see in the spectra the signature for plag and talc together. The talc unit is pretty yucky. It's texturally altered, pretty friable, bright, hummocky. There's not much going on here in like the majority of the spots. So it's frustrating, but we do think potentially in one region, the sediment cover, the friable material that's coming up sort of brushed away, but we still see this talc signature strongly. And there we do see these really bright filled fractures. And so on Earth, we know that talc forms in several different ways. And I've highlighted some of them here sort of in the context of our study. So the first being hydrothermal alteration of ultramafic protoliths. And so that, you get serpentization and then carbonation of the serpentine and maybe some talc that forms in association with that as well. The second is contact metamorphism of carbonate bedrock. And so this would be pre-existing carbonate-bearing sediments, say, that an intrusion, thank you, and goes into, and you get silica that interacts with that carbonate and makes talc. And then the last one on the bottom here is a bit rarer, where you have hydrothermal fluids that are interacting with potentially seawater. So these form on the bottom of the ocean, where you get talc precipitation in these talc chimneys. And so because we don't see, or because we see basically that talc is pretty spatially associated with the anorthosite, which does not provide a mafic component or the Mg that you need to make the talc. We don't think it's the first one on the upper left. And we don't see any associated carbonate in pretty much any of the pre-Noachian rocks. So we can probably rule out that it's contact metamorphism because we'd see the remaining lithology, the primary lithology. And so we need some sort of ultramafic source for hydrothermal fluids that are coming from depth and potentially interacting with surface waters. And so this sort of begs the question, how do these large impact basins like Hellas drive long-lived hydrothermal systems? And what are their implications for habitability, both on early Earth and Mars? And then I would say that is, pre-Noachian, maybe the next place that we should be looking for signs of ancient life as they preserve these big impact basins and hydrothermal long-lived settings. Thank you.
All righty, thank you so much. So we're going to move to our second talk with Matteo Loesch talking about transient alkaline lakes of Mars, the key to rapid oxidation. Take it away.
Okay, do you hear me? Yes. So hi, everybody. So today I'm going to speak about an idea, some hypothesis and some model we did about potentially some alkaline lakes on Mars that could be the key to a more rapid oxidation. But first of all, I want to explain why do we need a rapid oxidation on Mars, right? So the issue with Mars, and especially early Mars, is that you have this thick CO2 atmosphere. And when you equilibrate CO2 with water, you're going to have a rather low pH. And because of the dependence, because of the dependence of the oxidation rate to pH is more important than the one to oxygen, actually, it's going to hinder even more your oxidation speed. So even if we don't have a lot of oxygen, or even if we have a little bit, it's going to be the limiting factor is going to be especially the pH, which translates in very long oxidation, half-life oxidation of manganese and iron on Mars. For example, here, more than 10 years for iron might mean not that much for the Mars community, right? But we have to think about residence time and the mobility of element, and 10 years is quite a lot. It's a lot compared to Earth. And for manganese, it's even worse. It's like comparable even to the activity of water in some region on Mars. And it's why, before me, a lot of people propose, for example, bacterial catalysis, or like the Kaushik Mitra papers and team with alternative oxidants. And I wanted to explore if there was still a way to, oxidate iron and manganese, but still using oxygen. And the first observation on that is that we checked last year with a paper that indeed manganese and iron are very mobile and in a lot of conditions. So this is result from a sensitivity test of basalt weathering. So you have a basalt under CO2 being weathered, and we test a lot of different partial pressure of CO2 and of oxygen. And what you see here is basically the concentration. As more it's read, higher the concentration. And you see that iron is very mobile, even at very high partial pressure of oxygen. And for manganese, it's even worse. It's always mobile, basically, even at partial pressure of oxygen that are higher than on Earth. And so the issue with that is that we do observe on Mars iron oxides and maybe even manganese oxides. And for example, here I took this example of the Markarbon, the Amapari Markarbon in Gale Crater, where you see a succession of maybe very enriched layers in manganese and iron oxides close to siderite formations. And that suggests that there is a complex redox history, but we have a huge problem because we don't know how to oxidate these elements in a short time. And so my idea was that from the constatation that the issue is more the surface pH than the partial pressure of oxygen, we would need at the surface of Mars a new mechanism to explain a rise in pH. And to combine that with the high mobility of iron and manganese, I wanted to explore what happens when you evaporate a fluid and you consider an initial redox disequilibrium. So you start to evaporate a fluid that have still a lot of iron 2 and Mn2 in the solution that is ongoing in oxidation. And why evaporation? Because evaporation is a process that actually is going to change your pH. The pH evolve of a solution that is ongoing in an evaporation. And to summarize it here, I put the Tosca and Tutolo 2023 figure. And this pH change is related to alkalinity. Basically, if you build up alkalinity here, you're going to rise your pH. And this is going to be controlled by the carbonate solubility and carbonate formation. And in general, if you have less carbonate forming elements than alkalinity, that twice alkalinity, you're going to deplete these elements and build up alkalinity, raise the pH. And the opposite if you have less of these carbonate forming elements. It's very important to be noted, but in Tosca and Tutolo 2023, they showed that for kinetic reason, even when you go beyond the carbonate solubility, you can be hindered by kinetic precipitation and still raise your pH even though the alkalinity is limiting. And so what happens if you do the same thing, but you plug in redox kinetics and for manganese and iron? And so here we did many models, but I'm just presenting two. But the idea here is like you concentrate a solution that starts from a relatively dilute concentration, like river type concentration, and you do the oxidation kinetics at the same time that you concentrate. And what you observe here is that you initially raise the pH, and as you raise the pH, your iron is going to be oxidized completely. Here it's like iron oxides precipitating, which is expected because you are still at 10 millibar of oxygen. But on the other end, your manganese is start to be oxidized, but at some point it stops to be oxidized because you have the precipitation of carbonates. And these carbonates, they are going to remove the alkalinity of the solution, and you're going to lower your pH, and you don't oxidate much. You less than 1% of the manganese in the solution. But now, if you consider a perfect case where you remove these carbonates, you have a very interesting thing that happens is that the pH will rise, but continue to rise basically as you concentrate. And the pH is going to rise quite a lot, up to 4 units in pH, which allow this time the manganese to oxidate, and up to 30% of the manganese present in solution will form manganese oxides, which is quite significant and observable in situ, for example. And this without any change in partial pressure of oxygen. And so the next step we're exploring, and actually this model is already done, it's just that I did not have time to put it in the presentation. But when you plug in all the kinetics of carbonate precipitation, as you evaporate, you're going to observe this pH rising and an increased oxidation of manganese and iron. And so instead of having siderite and rhodochrosite, you're going to form manganese oxide and iron oxides. And we're building a setup to prove it as well, in addition to models. Yeah, I forgot to mention, we want to do sensitivity tests because obviously iron and manganese, they are like iron is much more rapid to oxidate than manganese. So they might have a different window of enhanced oxidation while you evaporate. And we want to determine that. Next up, why does this matter, right? So first, it's like in terms of theory, it matters quite a lot because for those who do evaporation research, you know that evaporation in general is dictated by what we call the chemical divide framework. Basically, you can predict your sequence of evaporate minerals based on initial composition of the fluid and the phase solubility. The issue is if you consider an initial redox disequilibrium, you could bypass such divides because as you evaporate, you rise the pH. So for example, instead of doing siderite, you're going to start to make iron oxide faster than you do your siderites, and then it's going to change your chemical divide, and that could snowball, for example, with rhodochrosite, etc. At the global scale on Mars, it could be also very significant because that would mean in some places where you think that the conditions are oxidizing but kinetically limited, as soon as you have evaporation and the right condition, you could have transient alkaline conditions that enhance this oxidation rate, which means that when you do modeling, for example, of steady-state lakes on Mars, that would change your parameters window where you actually do your siderites or your iron oxides. And that was in the Williams-Repan talk Tuesday, that we want to do this model and that we really need to consider this kinetic disequilibrium at the start, because if we don't, you would determine wrong parameters, basically. So my take-home message is that evaporation under the redox disequilibrium is more than likely on Mars. You will have weathering of your watershed, transport of your element in the water, and it will be evaporated, probably with still iron and manganese ongoing oxidation, with an ongoing oxidation by oxygen, because Mars is oxidizing, right, in some conditions, because we find oxides. And that, as we know it for now, evaporation seems to be a viable way to increase these oxidation speeds and get these oxides that we don't know yet, basically, how to form them because of the kinetic limitation. The next steps are so to determine this optimum parameter window, so partial pressure of CO2, of oxygen, evaporation rate, make the evaporation oxidation experiment. So the idea is really to show that these pH are rising, and instead of forming siderites, you're going to form iron oxides, but experimentally. And finally, apply it, as I said, on the theory, like redo a chemical divide theory, but considering this redox disequilibrium, because it's going to have a huge impact on the chemical divide theory framework, sorry. And finally, apply it to Earth and Mars models, because if you don't apply this phenomenon, it means the parameter you determine are going to be wrong. Thank you.
Okay, next we have a global spectral database of Martian compositional clay stratigraphies presented by Thanos Kleteros.
Hello, everyone. I'm really happy to share with you our work and this Mars Data Analysis Program funded work. And I want to give thanks to all my co-authors for helping put this project together. What we're doing is we're building a global spectral database of Martian compositional clay stratigraphies. If you don't know what those are, here's a really spectacular exposure of one in the Martha Vallis region. And what they are is they're a subset of Martian clay deposits where aluminum-bearing alteration minerals overlie iron, magnesium, phyllosilicate minerals. And here's a map of where they occur on Mars. They're typically restricted to like mid-late Noachian terrain, but there is some spread into some younger Hesperian units. And here's a 3D visualization using CRISM data to highlight the different kinds of alteration minerals you get. So in blue, we see the aluminum-bearing alteration minerals, and in red, the iron magnesium-bearing clays. We actually have a new paper that just came out in Geology a couple of weeks ago regarding these deposits. And what we are doing is using their topographic properties to test competing methods for their theories about how they form. So we actually found their topographic properties favor a subaerial weathering formation origin. And we measured their true thickness, so taking into account the strike and dip at loads of places on Mars. And we found really high values, but those are still similar to tropical weathering profiles on Earth. And why care about these? Well, if they form in a subaerial setting through weathering, then they therefore represent a really powerful record of surface, near-surface conditions on early Mars. And that's relevant to loads of questions that we have about this time period, like what was the nature of the atmosphere? When, if ever, were warm and wet conditions reached? What was the redox state and pH of surface, near-surface fluids? And all those geologic questions really feed into these key questions that we have regarding Mars habitability. We know now that early Mars did have habitable conditions in some places, but how long were those sustained for and how widespread were they really? And until we answer those two questions, we won't be able to know if Mars could really have sustained a biosphere. What are we doing? We're building a global spectral database. So in this Carter et al. 2015 paper, they published on finding 125 CRISM MRDR cubes that had this compositional stratigraphy, and our spectral pipeline performs all these steps, like continuum removed band center mapping. We're also extracting spectra from statistically generated high band depth ROIs. We're also extracting refined spectral summary parameters, the one that come with CRISM and the PDS data, to explore the association between these clays and other kinds of alteration minerals like sulfates or carbonates. And we're also identifying and mapping kaolinite-like spectra to evaluate weathering intensity. But how do we use this region of the infrared to discriminate between different alteration minerals? Here I'm plotting two kinds of minerals that are found in CCS, kaolinite and nontronite. And if we just take a look at nontronite, what you're seeing here is actually the average of all of the nontronite spectra in the USGS and Bishop spectral libraries. And something else I'm doing is calculating the continuum removed band center. That's the minimum wavelength where this band occurs, and actually taking a mean of the band centers of all these different spectra we have, because there is some natural variation that we want to account for. So that's what the vertical black line here is for nontronite, and you can see we've done this for a whole host of relevant CCS minerals. We can actually subdivide this region of the infrared then into like 6 or so groups based on band center. So For example, in cyan, we have this between like 2.2 and 2.22 micron band centers. We find montmorillonite, kaolinite, and halloysite, which are minerals of particular interest in CCS, but there's a whole bunch of other groups we can get. And actually, these final three, I actually took the band center bin straight from Michalski et al. 2015, which studied in detail the iron, clay, magnesium clay, and the intermixing that goes on there. So we have so much data. So I'm just going to show you the spectral database output from one single CRISM image. And this is a place in Marth Vallis, and it's a really excellently preserved example of a compositional clay stratigraphy. So the colored map I'm showing you now is the same colors as those different band center groups that I was showing you on the earlier slide. So we can see really interesting spatially coherent patterns in where these clays are located. And actually, this particular scene caught my attention because it seems to have, beyond just the ordinary aluminum and iron magnesium unit distinctions, there might even be some finer vertical zonation where it seems to grade from like an iron magnesium clay to a nontronite, then to things with band centers like montmorillonite or kaolinite, and then finally to things with slightly shorter band centers, which could be consistent with like allanite, badolite, or allophane. And the code extracts an average spectrum from all 6 of those classes for all of these CRISM cubes. I also just took a peek at the high-rise data because I was curious, and actually it does show really striking color variations with elevation. So that's totally consistent with the what the band center mapping from CRISM was suggesting. We can also look at this data in a different way. Here I'm showing a histogram, still band center wavelength, but now the y-axis is frequency. And we can see, at least in this CRISM image, actually, that a lot of the pixels in the aluminum unit actually have band centers that are slightly shorter than you'd expect for like a pure montmorillonite or kaolinite. There are still some pixels that are consistent there, but many actually cluster seemingly around like badolite or something like that. And that's an interesting thing we want to follow up with. We see it in a lot of CRISM images. Now I'm going to show some preliminary regional comparisons. So here I am showing the carbonate index, which is one of the refined spectral summary parameters. And what this is a violin plot, which is basically a histogram on its side. So the y-axis is mean carbonate index across that CRISM image. And each of these different colored blobs are different regions, the 5 regions that were in the Carter et al. 2015 paper. And what we find is different distributions. Now, most do lie above 0. So most of these cubes have values consistent with some carbonate present. But interestingly, Marth Vallis has a different distribution to the others. It has this high tail towards enriched carbonate. And that's consistent with earlier findings, which found carbonate in Marth Vallis and elsewhere. But we're interested in kind of exploring hypotheses for what that might be. Like perhaps, for example, maybe once all these regions had elevated carbonate values, but these 4 regions were subjected to like an acidic alteration event that might have leached those carbonates down. We don't see them anymore. Or perhaps it's reflecting different patterns in emplacement or even time. Like, for example, perhaps the Marth Vallis clay stratigraphy is older than the others, and it's recording perhaps older, more CO2-rich early Noachian atmosphere, for example. Lots of possibilities there. We've also had a quick look at regional variation in hematite band depths. That's a mineral that's a really sensitive proxy for oxidizing fluids. And we kind of find the opposite pattern, actually, where there's not much hematite in the Marth Vallis region, but actually clusters around Vallis Marinera specifically, and to a lesser extent, like Northwest Hellas. And so that's also an interesting avenue of exploration. And that map that I just showed you is already guiding a more targeted search, like intra-cube search for hematite. And I would recommend you all see Bryony Horgan's 2024 AGU abstract, where she looks into this in a lot more detail. And she's got kind of 2 hypotheses to test between, because they see kind of patchy hematite abundances. Could that represent like local zones of oxidizing conditions, like in ponds or something like that? Or could it actually be patchy preservation of a once much more widespread like hematite upper oxidized horizon to CCS that has been like variably eroded and preserved? So this talk was just really like a teaser. We have so much data, and here's a whole bunch of other prism cubes showing all the different phyllosilicate phases. So there's a lot more to explore. and more to come. But yes, here's my key takeaways. So CCS represent a key geologic record of surface, near surface conditions on early Mars and can help answer many of our outstanding questions. And we are developing a spectral database of them. Our preliminary findings show that the strongest evidence of carbonates are in the Marth-Vallis region, and they seem particularly associated with the aluminum unit, which is interesting. Whereas hematite band depths are strongest around Valles Marineris and Northwest Hellas. So coming to a journal near you, hopefully, is all these products for the 125 Carter et al. 2015 CRISM cubes, and also our spectral pipeline code will be published alongside that so you can replicate findings and explore them yourself. Thank you, everyone.
All right, and then the last talk of this little section is going to be on global mapping of hydrous minerals associated with hydrothermal and a metamorphic alteration on Mars by Oscar Camps.
Hi, it's good. Can you hear me?
It's supposed to be in person.
I think he's trying to share over Zoom.
Hi, can you hear me?
Go ahead, Oscar.
Okay, thank you very much. Yeah, sorry, I was supposed to be in person, but had to change plans. But I'm happy to take this opportunity to discuss our work on global mapping of hydrous minerals, and especially the ones associated with metamorphic and hydrothermal alteration. I'm a postdoc researcher at Caltech, and I work under supervision of Bethany Ehlman. Next slide, please. So we start this work with our this main research question: what does the global distribution of minerals associated with particularly hydrothermal and/or metamorphic conditions reveal about the past geological environments on Mars? And these include temperature, water, chemistry, and geological setting. Next slide, please. On this slide, I've made a short selection of a few minerals that are often mentioned in literature in relation to hydrothermal or metamorphic alterations, and some citations refer to it. The difficulties with most of these minerals is that they don't form just by hydrothermal or metamorphic alterations, but they can also form under other conditions, for example, surface weathering. Next slide, please. These diagrams, these are from the Bethany Ehlman paper from 2011. And in the red boxes, I highlight the areas and the conditions where prehnite is formed. From the previous slide, you've seen the list, and we focus on prehnite in particular because it forms under very specific conditions. And these are temperatures between 200 and 400 degrees Celsius. And a low CO2 fraction. That this mineral forms only at these specific conditions makes this mineral so interesting to map out. Next slide, please. We have chosen to do the global mapping based on the targeted images, and particularly the ones between 60 degrees latitudes. The mineral itself is mapped already locally in specific areas, for example, in Nile Fosse, but this is the first time it's systematically mapped globally. We have chosen for the CRISM data because the wavelength range in particular is very good to detect hydrous minerals, as you have seen in previous presentations. And we chose for the targeted ones because the mineral forms very locally. So the high spatial resolution makes it good for local outcrop detections. As you can see on the right, we have the center location of the targeted images plotted on a global map. Although we have a global distribution, we don't have a global coverage. So it's still some places that were not mapped by the targeted images. In total, we have mapped around 10,000 images or analyzed to see if there is prehnite or not. Next slide, please. This image shows a few spectra and a few good spectra from the CRISM data. And I chose those three because these are often grouped together. And these are in blue, the smectite mineral, in green, the chlorite, and in orange, brainite minerals. As you have seen in previous presentation already, for example, smectite, and especially the iron magnesium smectites, they have a wavelength around 2.3 micrometers. Chloride and brainite, a bit to the longer wavelengths, around 2.35. The difference between chloride in the 2.3 region, they look very similar, but the difference can be, they can be separated from each other based on the 1.48 feature. So that's the shorter wavelengths. Problem is that it's often a very shallow feature, so hard to detect in the data. Next slide, please. This shows the workflow of that we are using to create final mineral maps and our confidence that we detect this brainite in this case. So we create final brainite mineral maps. I will go through each of these steps. So please, next slide. In 7 spectral regions, we look for the deepest feature in that region. So the regions are indicated in the gray boxes. For each area, we do a convex hurl removal, and we search for the minimum location and calculate the deepest feature and the wavelength position. Next slide, please. And another time. Here you see, for example, for a specific one image, on the top row, the depth feature values for a feature around 1.4, around 1.45 and 2.3, and on the row below, the wavelength positions. These are used as an input for a decision tree classification model. Next slide, please. And again. So this is the final outcome of one of these images, indicating the likelihood of brainite. The warmer colors, the more yellow, it's a higher confidence and also higher presence of the features of brainite. It's a normalized average between the 1.48 and a 2.35 feature. On the right, you see a false positive detection. So we have to deal with some noise, and that therefore we still do a manual check if with the spectra, if we detect if it is brainite or not. Next slide, please. This is our initial global map. It's a preliminary result, and we are presenting in the center IDs or center locations of the different CRISM images where we think there might be brainite on Mars. In the purple, you see the ones with high confidence of brainite detections, and in orange or in pink, the ones with a lower confidence. This can either be that it has a combination of features, so we're not sure if it's a mixture with other minerals or if we are detecting another mineral. What you can see is that it is the most detections are clustered around Nili Fossae and in Terrena Terra. Next slide, please. For these regions, I made this zoom in, showing the outline of the CRISM IDs or the CRISM images. Same color scheme, and you see that most clusters are around craters. The ones around Nili Fossae are very well described in literature already, but around Terrena Terra, we think we detected a few. We have a few new detections. So future work includes checking what this means geologically about these conditions. Next slide, please. Some of the images that we with brainite detections have overlapping CRISM images, and this gives us the opportunity to check how well our algorithm is working. So on the top right, you see two images which we identified as low confidence, and on the lower right, overlapping images where we have a high confidence of brainite detections. The color indicates the values, the depth values of a feature around 1.48 micrometers. And you can see with a high confidence that these areas, the higher, the warmer colors overlap very well. But in the ones with the low confidence, we see a spatial correlation around the crater rim. But also there is quite some noise in the data that you can see in the with high values along the column. So just based on the depth values, it's hard to distinguish between noise and a spectral feature. So that's what we're still working on to see if we can better make a signal to noise ratio to better identify if we are looking at a feature or noise in the data. Next slide, please.
30 seconds.
Oh, great. I will end with the conclusions. So we have produced a global map of brainite. There where we have been successfully detected shallow spectral features, especially the ones around 1.48 micrometers. Brainite, it seems, based on our preliminary results, it's not widely spread on Mars, but clustered in specific areas, especially nearly Fossae and Terrain Terra. Currently, we're assessing the geological similarities and differences between brainite clusters to understand the formation environments. I will end with this. If you have questions, you can find my email below, or I will join the panel discussions.
All right, thank you.
Thank you.
All right, can our last four speakers, I guess the first three, come to the stage? Anyone who has questions, please come up to the mic or type them into the chat. Just remember to say your name and affiliation.
Jim Head, Brown University. A question to Dr. Viviano. So really excellent talk. It's great to see a stratigraphic approach to this. Just another thought for the talc alteration processes. Ashley Palumbo and I published a paper in 2017 in Meteoritics and Planetary Science, which talks about the aftermath of an impact in terms of the atmospheric effects. And in that case, there's very hot rains that come down for weeks to maybe months, okay? And this is another process that could easily mimic something like hydrothermal alteration. So I just encourage you to take a look. I'll send you a copy of the paper, but it's something that's potentially really important in the context.
Okay, excellent. Thank you. Yeah,
Okay.
that sounds really interesting, and especially in the context of the big basin and the proximity of it to the basin. Appreciate it.
Carlos Garibicas, Louisiana State University. So I actually have one question for Oscar and one for Thanos. So I'll start with Oscar. Oscar, when you're looking at these, high confidence brainite detections, have you actually looked at the geomorphologic context of these detections? Do you have any intuition as to if there's any geomorphologic evidence at these sites for what process might be forming it?
Good question. We just started working on projecting the data sets and compare with, so map it out. It seems that most detections, the ones at least where we are very confident in, are related to crater geomorphology and often ejecta blankets or around crater rims, indicating that it comes from a deeper, so in the subsurface. But yeah, we're still working on to do it more systematically.
And then for Thanos, I understand that the paper is kind of like in preprint, so I haven't been able to actually read it. But have you also tried to look at the regional context of like the actual composition? So looking into the thermal part of spectroscopic analysis to do bulk compositional assessments for all of these locations, or are you just sticking to near infrared for now?
No, actually, I haven't thought about looking at the thermal data, but that would be an excellent way, like characterizing the protolith underneath them, perhaps like the unaltered regional bedrock. I think that's a great idea as an avenue of research. Thank you.
Hi. My question is about the composition stratigraphy too. So one of the things we had noticed was that every once in a while you would see jarosite sort of draped or sort of an acid, materials draped on top of the aluminum phyllosilicate kaolinite rich layer. I was just wondering if you were seeing any of that happen, or have you found any more instances of that?
That's a great question. I know that Samantha Baker is really interested in the jarosite and the implications its association with the aluminum unit. Like they had a poster on this on Tuesday evening on the Northeast Syrtis region. I haven't looked too much myself, but with the band, we're doing the band center mapping, and it is one of the phases we're looking out for. And we do see actually in some places alteration minerals on top of the aluminum unit. So it's not common. Usually, like for example, in Marthalis, the sequence is capped by an unaltered mafic dark capping unit. But there's a couple patches where I've actually seen like a saponite horizon overlying aluminum unit, which is uncommon and indicates a kind of regression to a more reducing environment. So yeah, definitely interested in what's going on at the top of the stratigraphy as well.
Coming over here so I can actually see Matteo. Matteo, I wanted to ask you, when you do kinetics, as you full well know, it's not always that easy. Have you considered hydrous phases like hydromagnesite and then magnesite, or will you consider them, or are you just going for plain minerals for now?
As you know, if you give me the kinetic rate constant for hydromagnesite, I would do it, of course. But I think it's a valid point, and what I think I forgot to say it in my talk, but actually we don't even need to consider precipitation kinetics if the solutions on Mars were, having more alkalinity than 2 times your cation content. You don't even need to invoke any kind of kinetic inhibition or slow kinetics to get your high pH. But I mean, again, we need to wait for more results, but so far from the model, we do it with just the rhodochrosite, calcite, magnesite, and siderite. Calcite is the fastest to form, and still in a ponding environment, when you are speaking about the wicks, basically, even calcite is rather slow to precipitate, and your pH is going to rise quite a lot. But for hydromagnesite, I don't know, to be honest.
No, I was just thinking because we found that in some experiments and we're like, ooh, oh.
Really quick reminder to say your name and affiliation before you ask your question.
Janice Bishop from the SETI Institute, and I had a question first for Christina, and I loved seeing your results in your map, and this is great to see such feldspar detections, and I was wondering if you see a correlation with this feldspar and aluminum phyllosilicates, because you were mostly talking about magnesium today.
Yes. Yeah. And those have been previously talked about in the literature as well. There's a lot of kaolinite that's associated with the plagioclase. And you can even see like at the pixel level kaolinite with the 1.3 iron band in the plagioclase. So yes, absolutely. That's there.
And I would also think maybe if the clay minerals formed, then there'd be less plagioclase because it got altered. But I don't know if there's.
It's patchy.
Yeah.
So some show it, some don't. It's not like abundant, I would say. Yeah. Yeah.
And I also have a question for Kildaris. I didn't quite catch your.
Thanos Clidaris.
Okay. And I was wondering about your carbonate maps. If you could tell us, if you could describe which band centers you're using for that, or how you're verifying your carbonate detections.
Yeah, I'm actually just using the Viviano et al. 2014 C-index to refine spectral summary parameter. But actually, co-author Bill Farrand is actually using these preliminary C-index 2 results to then do a more detailed search for carbonate using the longer wavelength carbonate features that are sort of outside my range. But yeah, he's definitely the one to talk to for that kind of data.
And I would caution you for mapping based on those alone, and especially carbonate's really tricky. And I don't think you should trust your detections until you actually go look at the spectra and the shapes, and a lot of other things could be there that could be misidentified.
Great, that's good to know.
Hi, Adrian Burrows, Purdue. I had a question for Christina. First of all, great talk. Dr. Bishop actually kind of asked the first part of it about the aluminum clays and their associations with felsic stuff. But to build on that a little bit more, I'm wondering, do you see any associations with kaolinite and talc or other higher temperature hydrothermal-like minerals, or is it mostly the case where the kaolins are associated with like lower temperature stuff? Or yeah, can you elaborate any more on that? Thank you.
Yeah, I don't know if I can comment explicitly on the temperature per se, but in terms of the distribution, they're both associated with that Plage unit. However, they're not necessarily like in the same locations. I don't think, if I'm remembering correctly, that I ever see mixed spectra with kaolinite and talc features. But yeah, I appreciate that. Thanks.
Yeah, yeah, this is Bill Farron, Space Science Institute. Just add to what Thanos was saying and respond to Janice Bishop. You know, yeah, he's just using the C-index 2 parameter, and you know, it's still a work in progress, but trying to use a factor analysis target transformation to narrow down to confirm the presence of carbonates. So, thanks.
Aria Udry, UNLV. So this question is for Christina. It's not really about alteration, but about, you mentioned in the mid-Noachian, if I'm right, that olivine content has been increasing compared to the pre-Noachian, the early Noachian. Could you develop more on that? Did you see it in a different location? Or like, I'm interested because we see that in igneous rock. So
are you saying in the, I didn't catch the dates. So the mid-Noachian compared to early and pre, or?
Yeah, there's more that you found, more olivine. Is it considerable? Is it?
Yeah. So I guess it's hard to say that this would be like a global phenomenon, because it's definitely related specifically to Isidis and surrounding Isidis. So I don't know if it's just like locally there's this, you know, enrichment and olivine that's in the basement rocks that are being exposed, or if it's a unit that, you know, is global. But yeah, I mean, we see olivine throughout the Noachian, and there is some in pre-Noachian as well. And I think Michael Phillips' talk a little later in the session will probably get a little bit more at like the distribution of the primary lithologies globally. Might answer your question better.
Thank you.
Yeah, thanks, Aria.
Steve Ruff, ASU. Christina, you sort of closed with the idea of the habitability of potential impact hydrothermal, which is just another example that has prompted me over the years to think about whether or not, and I don't know if there's really literature on this, impact hydrothermal equals volcanic hydrothermal in the context of habitability, right? So, you know, the distinction is that volcanic hydrothermal, there's typically gases evolved from the magmas that go into the fluids, and the fluids are what drives typically the microbial, short of photosynthetic metabolism. You're talking about chemosynthetic metabolism, which is derived from the fluid composition. So that's a long preface to, you know, are there, and I'm just floating this really because I don't know, you know, are there minerals that one could recognize in a known volcanic hydrothermal context that make that a habitable environment that then you look for in an impact hydrothermal, and the absence thereof maybe makes it less habitable or something? So you are someone who could potentially sort of be looking for those associations with, you know, CRISM data, and I don't know what they are, but floating it.
Yeah, no, those are great points. I think, gosh, I don't know how we'd fully wrap our heads around it, but yeah, certainly they're going to be different environments that are producing different alteration materials and fluids that are coming up that are different from a volcanic setting. I think also the longevity of these make me think that anything that is in the subsurface, like, you know, groundwater, ice or whatever, could also contribute to these as well. So I don't know. I hate to like try and pin it down. So I think it's probably a pretty complex situation given the time span and the complexity of the subsurface for one of these. But I really appreciate the comment.
Well, and it is complex, and that's why I'm hoping that someone will
Yeah.
take this up, and
That's
maybe
good.
it should be, but just it's too easy to say hydrothermal, and is impact hydrothermal
Right.
equivalent to volcanic hydrothermal in the context of habitability? I don't know the answer. So someone needs to figure this out.
Thanks.
Hello. We've got a question for Oscar. I think you moved a little quick over, and I didn't quite catch what the you introduced the pre-night by saying it had a quite constrained PT space that forms, and I was wondering if you could elaborate a little bit on precisely where that is and what the implications are of the spatial distributions that you're seeing for broader processes.
Yeah. So the conditions which is formed. So prehnite is in the general metamorphic phases diagram that we were also showing in our presentation, the pressure against temperature. It's relatively low pressure, but high temperature between 200 and 400 degrees Celsius. And on Earth, it's often related to the prehnite pumpelite phases, sometimes also called the subgreen schist phases. So what it means depends. It can either form because of diagenesis and burial metamorphism, so that the temperatures are higher, deeper in the surface, or hydrothermal, so that higher temperatures are caused because of volcanics, and that can be either impact melt or it can be a volcanic source. And that's what we try to figure out. But for that, we need more, and we're working towards a more spatial context.
Do you think you can discriminate between those different formation environments given correlation to geomorphology and or other minerals?
I think we have to see, but based on what we have, the results we have now, it's sort of surprising that it's only formed at certain regions. And if it's deeper, and I'm now just thinking out loud, if it's formed deeper in the surface, you would expect it on more areas on Mars, and not just, and that it brought to the surface where there are bigger impact craters. But what we see so far is that it's also detected at some very small impact craters, which means that the prehnite or the high temperature conditions were not that deep. So yeah, we have to, we'll work on that to see what that means in that context.
Thank you.
Hi, S.J. Ralston, they, them, Mentum at Johnson Space Center. My question is for Matteo. It's really interesting work, and I agree that carbonate kinetics are going to be really important for understanding all this. Have you looked into, or do you plan to look into, how degassing of carbonate or exchange with a CO2 atmosphere would affect these results with regards to how carbonate alkalinity would change in those circumstances?
So it's a bit long to explain exactly what happened, when you build up alkalinity and you rise the pH, but it's basically this shift in the carbonate buffer system, and I don't think would be any interaction. I mean, so you need obviously space to degas. That's you need it, but the fact it's CO2 atmosphere would not change anything for the increase in alkalinity. For the rise in pH, but of course it's because of the CO2 atmosphere that you have low pH in the first place. I don't know if I answered the question properly.
Yeah, it's good. Thank you.
Alrighty, and that ends our first Q&A. So let's thank our speakers one last time. Next up is Lucy Thompson, and she's going to be talking about the composition variation within Geddes Vallis deposit, Gale crater, implications for province, depositional process, late fluid flow, alteration processes, and more.
Okay, hi everybody. I apologize in advance, sorry, about my voice. Hopefully it'll hold out. I'd like to thank my co-authors and the whole MSL team, and also in particular the Mali and Mastcam teams. So we're in Gale crater, and before we landed, this feature of interest was identified from orbit, Geddes Vallis Canyon, which incisors the Yardang unit and the sulfate unit at the central mound within Gale crater. And because it incisors those units, it's interpreted to be relatively young. So we wanted to investigate the Geddes Vallis Canyon and its associated deposits to determine what processes were involved in the formation modification of the Geddes Vallis system. What was the role of water? So can we identify evidence for it, the amount, duration, and timing? And what was the source of the sediment that was deposited within the Geddes Vallis Canyon? On the right here, you can see this is the rover's traverse. We traversed through the Bradbury group, and then we started to climb the Mount Sharp group when we got to the base of Mount Sharp. And then you can also see locations where we investigated the Stimson Formation shown in blue here. And I'm going to zoom in here and discuss the results of APXS compositional analysis of the Geddes Vallis deposits and discuss what that can tell us. Okay, so zooming in, we investigated the Geddes Vallis deposit here with float that we found in situ here at Bubacas. And then finally, when we crossed the deposit here, which is shown in more detail, and again, I'll just highlight the Stimson Formation where on green hue pediment here, which is not that far away from where we investigated the Geddes Vallis deposit. So the APXS results. We identified, excuse me, sorry, 6 compositional varieties of material within the Geddes Vallis deposit, and I'm going to go through them on this calcium CaO versus SO3 plot, and I'm going to discuss them relative to the sulfate unit bedrock immediately outside the channel, which are these yellow squares here. So first off, we have group 1, which I've highlighted in red here, and you can see that it has low to moderate sulfur, and the calcium is trending high compared to the bedrock outside the channel, and it overlaps the composition of the Stimson Formation in blue, the Bradbury group in purple, and soil, which are those grey crosses in the background. Then we have group 2 in pink here, and group 2 overlaps the Mount Sharp group below the sulfate unit, which are these pale orange squares. So you can see that we have lower sulfur, but around the same calcium as the bedrock outside the channel. Then we have group 3 in green, which you can see overlaps the sulfate unit outside the channel. And then we have group 4 in gray, which also overlaps the bedrock outside the channel, but is trending to higher calcium and somewhat higher sulfur. And then we have group 5 here in white, and you can see we've got high sulfur, but we do not have correspondingly high calcium. And then finally, shown here in yellow, is group 6, which is the elemental sulfur, which hopefully you all heard about this morning, which obviously plots off this graph. Okay. So this plot of calcium CaO versus P2O5 just quickly illustrates that group 4 material which is trending to the higher calcium and sulfur compared to the bedrock outside the channel, which are those yellow squares outlined in gray here. That trend high calcium correlates with phosphorus. And again, we're just seeing the groups on this plot of MgO versus SO3. So again, group 1 is overlapping the Stimson Formation and the Bradbury group and soils. Group 2, again, is overlapping the sulfate unit below, the Mount Sharp group below the sulfate unit. And group 3, you can see is, although it has the same sulfur and calcium as the bedrock outside the channel, the magnesium is significantly lower. And again, group 4 is close to the bedrock outside the channel, but trending to higher sulfur and somewhat lower magnesium. And then we've got our group 5 again with that high sulfur, which again is not showing kind of high magnesium. So the magnesium and the calcium are not elevated, associated with that high sulfur, and none of the other cations are either. And then finally, again, group 6 plots off here. I'm going to skip over that slide. So what are the field relations? What do the rocks actually look like? And how do these compositional groups, vary within the deposit? So I'm going to focus in on some key locations. We've got Bubacas here, which was our first in situ investigation. And then I'm going to focus in on these locations at the crossing. So White Bark Pass, Kings Canyon, McDonald Pass, and Lucy's Foot Pass. So Bubacas is the type location for the Stimson-Bradbury-like composition blocks of group 1 seen here. And this is interpreted as a debris flow deposit. At White Bark Pass, what you can see is we've got a block here which has a group 3 type composition, and it's rimmed by gray type 4 material. And down here, there's actually some lighter tone type 5 material. And you can see that this is in close association with these elemental sulfur blocks. Okay, at Kings Canyon, we also have this gray and light toned material, group 4 and group 5 materials rimming this large block, which has a type 2 composition. So we've got that rimming material on the type 2 and type 1 material. Okay, McDonald Pass is similar to White Bark Pass, where we have type 3 slabs rimmed by the type 5, type 4 and 5 materials, but we don't have the elemental sulfur. And then finally, Lucy's Foot Pass is a really nice example, especially if you look at this close-up Marley image on the right-hand side here. And you can see this coarser gray material and this smoother kind of purpley material. And the composition of this block and those textures are consistent with a type 1 Stimson-Bradbury-like material with a coating of the type 4 gray material. So that type 4 coating and rimming material occurs on types 1, 2, and 3. And it's pervasive throughout the deposit. Okay, so what does all this mean? So we interpret the APXS compositional classes to be attributed to differences in provenance and secondary alteration processes. So provenance, we have 3 distinct sources for classic material: a Stimson-Bradbury-like source rock corresponding to our group 1 composition, a lower sulfur clay bearing, we drilled it, a source rock with similar composition to the Mount Sharp group below the sulfate unit, and then materials similar to the sulfate bearing unit outside the channel, and it had sulfate and carbonate minerals in it when we drilled it. So where are these from? So the Stimson, there may be an extension of the green hue pediment Stimson-like formation upslope, which could be contemporaneous with Bradbury group, or it could be something else that just has a similar depositional setting, provenance, and or diagenetic history as those groups. And we haven't actually seen an obvious source for that. I'm running out of time. We have seen chrism clay signals higher up on Mount Sharp, which we're hopefully going to visit. So hopefully that's from B. And then obviously we think that the type C material is locally derived. And I'm going to skip over that for the minute and quickly go to what we consider to be the source secondary alteration processes within the Geddes Vallis deposit. So those are the type 4 and type 5 materials, and they occur as rims and coatings. And in particular, the type 4 material occurs on all 3 class types. The type 5 material is almost always associated with that type 4 rim material and is also often in proximity with the elemental sulfur. And then we have the elemental sulfur. So the rimming material, right, I'm over, I think. Anyway, the rimming material appears to be pervasive, and there's elevated sulfur associated with it, which we think means that maybe there's some relationship to the elemental sulfur. And hopefully you heard the talks on the elemental sulfur this morning, and I'll leave it there. Thank you.
Thank you.
Okay, great. Next, we have Jürgen Schieber, talk on mostly aeolian or lacustrine, a sedimentary and petrographic perspective on the depositional setting of upper Contigo through Chinapao strata, Gale Crater Mars.
Okay, doke. So even so, the marker band, which is going to go through here, is of course the most exciting unit. My colleagues and I have decided to look at the rocks maybe 10, 20, 30 meters below and above the marker band to see its broader depositional context. Okay, so where do I transport the slide? The big button? Okay, so the popular view about the marker band is that it's an intermittent lake that formed in a mostly Aeolian setting. Our alternative interpretation is maybe a lacustrine mudstone. There was a long dry spell which caused alteration of the surface sediments. Then the lake returns, you get basal scours and all this kind of stuff. So you get the ripples. The lake deepens, you get the rhythmic unit, and things get to normal lacustrine deposition above that. So it's quite a bit different. And so the reason why we think so is that it's really difficult in any Mali picture of Mirador to see any sand grains. We see sedimentary attributes that are seen in earlier encountered lacustrine laminites. And also the chemin data suggests some mudstone affinity. And we also see parasequence stacking and stuff like this that's typical of mudstone successions on Earth. And so the models are basically that we have here is, this is a community model, and this is our alternative model where we look at primarily lacustrine setting, but maybe with some Aeolian intervals interspersed with it instead of the other way around. So talking about the first point, the lacustrine laminites, these are laminites that we saw at Parum and at Hartmann's Valley, and you see these lamina that are those hardened lamina that have the little crystallites in it, which are basically evaporite pseudomorphs. We see very similar kind of stuff here at basically roughly in this area here. And then you see it also above the marker band, up here. You see again these nice lamina. And here we have this lacustrine appearing lamina 160 meters above the marker band exposure. And it still looks very mudstone-like and like the other ones. So the sedimentological perspective is that an Aeolian interpretation of the Mirador is compromised by a general lack of visible and identifiable sand grains in abundances that we would expect to see in a sandstone. If the second point is that the Mali close-up examination suggests a common presence of mudstones, and the fact that in multiple places these mudstones closely resemble lacustrine laminated mudstones that essentially everybody on the MSL team has agreed upon also works against this. So, and then we have also a perspective based on chemin data. And we're looking at just a few examples I'm listing here. We have basically modern material from the Bagnall dunes. We have the Kimberley, Minjana sandstones, and the Stimson Big Sky sandstones. When you look at it mineralogically, about 2/3 of these samples are always silicates, mainly feldspar, pyroxene, olivine. And then about the rest of the rock is amorphous plus a variety of minor phases. And you can always see the sand grains. If we go to the next material here, this is a bona fide lacustrine mudstones from Parum. And you see here that the Parum mudstones have less than half to a third silicate minerals, feldspar, pyroxene, olivine, of course, silt size now, and then half or a little bit less than half is amorphous material and other phases. So you have sand-sized particles in there, but they're scattered through along the lamina here, and we interpret them early on as not detrital grains, but as pseudomorphic evaporite minerals, and the XRD data again supports that. So if you sort of look at it more broadly, you have here earth sandstones, typically about 2/3 silicate grains, Gale sandstones about 2/3 silicate grains, and then I say poor matrix means, and in Gale, of course, that means the amorphous stuff and the miscellaneous phases. There are usually a little bit clays in there, and there's always sand grains visible. In the Gale mudstones, on the other hand, it's always a significantly low amount of silicate grains, which are silt size, and we have the amorphous matrix plus minor phases about 1/3 to half. There's a distinct difference between the sandstones on Earth and Gale versus Gale mudstones. If you then look at the Mirador samples, Zechstein, Navarro, Canaima, you see relatively low contents of silicate minerals that are the grain formers typically in a sandstone. And then you have lots of amorphous stuff, no clays, and no visible sand. From a chemical perspective, the Mirador strata more closely resemble a Mount Sharp mudstone and are unlike clearly identified Gale sandstones. Okay. So next. Now, some people have said, oh, you can't see the sand grains anymore because they've been altered to bits by post-depositional alteration. The only problem with that is that when you react the basalt if you react a basalt at low temperature in a range of potential martial water compositions, we tried quite a few of them. It's always a lot of smectite, some chloride in all runs. So it's basically you form clays. There's no escaping from it. On Earth as well, you alter basalts, you get clays. And so the Mirador rocks contain no clays whatsoever. And that therefore does not support or suggest a significant alteration of basalt-derived silicates. Okay, so that is the argument against alteration and disappearing of sand grains. Another aspect that we observed just below the marker band, like here's a marker band, okay, here's the altered zone below it. If you look at stratigraphy underneath it, it's a succession of soft to hard, soft to hard, soft to hard packages, and which is also marked by the dying out of fractures in the softer intervals. What this reflects to me and my colleagues is that we have pulses of classic input, infill accommodation, and then we get increasing cementation towards the top of the parasequences. On Earth, this works both in marine and lacustrine settings. It's a fairly fundamental concept. It's universal. You don't need to be on a different planet for it, but you can if you want to. And here's just some examples of how this looks like on Earth from the Jurassic. You see very nice parasequence stacks. They're always cement towards the top. And here is a Precambrian example from Australia. This is what somebody that works on mudstones for many years sees all the time in mudstone successions. That's how they stack up. And this matches very well with this here. So basically, this is yet another reason to think of the rocks or the succession being dominated by mudstones. I'm not going to exclude that there's sandstone interspersed with it, but it doesn't have to be. Okay. So here, just briefly, history of the marker band. We have, let's see, here we go. We have basically these lacustrine lamanites. There's inflow of water and sediment dwindles and stops, lake shrinks and dries out. We get salt crusts and desiccation cracks, like this stuff here. This is on Mars. This is an Earth example, an exposure surface with a paleosalt basically forming underneath it. And so these altered zones and salt crusts are common features associated with sequence boundaries in lacustrine systems on Earth. And given that chemistry and physics don't care, it should be on Mars the same thing. And then the marker band deposition itself, we have basically the return of the water and sediment that gets carried deep into the salt flat initially. You get basal erosion that scours, shallow water, wave ripples forming, lenticular bedding, and all this kind of stuff. And then as lake level rises, sediment supply to distal area decreases, deeper water, lack of sand means no more wave ripples, and then we go back to these hard to soft couplets that get successively thinner as we go up, and then finally we end up in the last part of it where these millimeter laminites look pretty much the same as you looked before at the very base of the succession. Okay, so we go back into high stand laminites. So in conclusion, we think it's mostly lacustrine mudstone in that succession instead of sandstones. And because when we examine in detail, mudstones are based on visual and chemical data. Sand grains are not common. And the Aeolian setting for the mirror deformation is not consistent with available data, at least not the prevalent Aeolian setting. The Mirador strata have many of the sedimentary attributes associated with lacustrine laminites, and the parasequence stacking and mechanical stratigraphy is analogous to cyclic sedimentation patterns under mudstones. So the underlying Mirador strata are mostly lacustrine. The marker band presents a transgressive system stacked overlying lacustrine sequence boundary. The overlying millimeter laminites are mostly lacustrine as well.
Right, we're gonna have to stop. I'm sorry.
Well, I'm done anyway.
All right. Up next, we have Lucia Mandan talking about diagenetically altered fine-grained sediments at Nereida Vallis on Mars.
Good afternoon. All right. Okay, so after hearing news from the Curiosity rover, today I'll walk you through the composition of a unit that was investigated by Perseverance this time, and I really caught our attention last summer. And so if we go to the next slide, you will see that after exploring the igneous floor of Jezero crater and these sedimentary rocks of an ancient delta, with Perseverance, we explored some light tone, likely sedimentary rocks on the floor of Nereida Vallis, which is this large river valley dissecting the rims of the crater. And so these light tone deposits, which we informally refer to as the Bright Angel Formation, they outcrop in the north and in the south flank of the valley. And so here the team identified some key indicators of past habitability and prebiotic chemistry in the form of phosphate reduction spots and complex organic matter. So there is a real interest in understanding what these rocks actually are and how they form. And so if we go to the next slide, you will see that we used the full SuperCam instrument suite to characterize the Bright Angel Formation. So that means a frequent analysis of rock targets that were from about 2 to 8 meters away from the rover mast. And here we have a synergy of techniques, including color imaging, laser-induced breakdown spectroscopy, or LIBS for elemental rock composition, and investigation of mineralogy from visible reflectance and Raman spectroscopy. In the next slide, you can see some example of color images of bedrock exposure of the Bright Angel Formation. So you can see it is a low-lying fine-grained bedrock with extensive light tone vein. At some localities, we also observe some concretions. And one particularity of the bedrock in the southern area, as you can see in the upper right example, is the presence of embedded clast and a notable reddening of the bedrock. Now, in the next slide, you will see a summary of the chemical composition of the bedrock from LIBS analysis. And the first thing we see is that this composition is strikingly different compared to the bedrocks that were previously analyzed during the mission, in a sense that it is relatively high in silica and it has a very low magnesium content. If we look at this ternary plot of different major oxides, so we have our measurement in the northern array in pink and the southern array is in orange. And we can see that the Bright Angel Formation plots relatively far from the gray clouds of higher iron and magnesium, so mafic rocks that characterize most of our traverse so far. And instead of mafic rocks, what we see here is a bedrock mostly enriched in some aluminosilicate phase. But we do also have some scatter with a few measurements of more iron-rich phases that have a stoichiometry close to a non-tronate. We see some scatters around our typical dust and coatings compositions. And we also have some scatter toward the alkali apex, which I'll come back to in a minute. Now, if we look at minor elements, and this is the work of Henry Manelsky and Wolf, who have posters at LPSC this year, they also showed strong enrichment in nickel, so up to the weight percent, which has never been measured to that level on Mars before. And also some phosphorus as well as fluorine enrichment, which is likely present as fluoroapatites and fluorides. Now, if we go to the next slide and come back to that scatter towards the alkali's apex, here the lips and Raman are positive to calcium sulfates, and they are present both in the matrix as fine grain and in the light tone veins that cross-cut the bedrock. Here we see sulfur emission lines in the lips measurement where calcium is enriched, and we also see some sulfate peak in the Raman spectra. So next slide, coming back to the bulk of the rocks. Some of our measurements, and especially in the south of the valley, show a relatively high aluminum and high chemical index of alteration, which is a proxy for cation leaching, so evidence for some open system aqueous alteration. And in these rocks, potassium is also quite high, and the major oxide compositions trend towards illite. And this is interesting because elitization relates to diagenesis processes. So next slide, please. So with this IR spectroscopy, what we saw was relatively similar between the south and the north with some slight variations. We have relatively weak hydration bands. We have some drop of reflectance past 2.3 micron, likely related to sulfates. And the spectra also show a 2.2 micron, so aluminum or silica wedge band, and that seems to be deeper in the south, so here in this pink spectrum. And this could agree with elitization because ilites also have a 2.2 micron band as well. Now, if we look at iron, we see the signature of a ferric oxide in the visible, and we also observe a very weak band at 2.28 microns, so an iron 3+ wedge band that could be explained by nontronite or perhaps jarosite, but it's a bit less convincing. And finally, we also had hints of a 2.46 micron band that could be indicative of akaganeite, which is an iron hydroxide. So now coming back to this signature of ferric oxide in the visible range, in the next slide, we can have a look at a parameter that quantifies the strength of this signature. And what we see in this plot is the evolution of this parameter for abrasion measurements over the course of the mission. And what we see is that the abrasion in the south area has yet the strongest signal of ferric oxide on an abraded surface at J0 so far. And that is what is giving its red color to the southern bedrock, which is strongly oxidized. You can see on the left that the last time we saw a similar signal was at the front of the deltaic fan on a target with hematites. Now going to the next slide, you will see that the southern region gets even more interesting as we looked in the upper part of the stratigraphy. Here we observe some iron-rich compositions, and the VSR spectra are consistent with jarosite. You can see on the right that most of the diagnostic bands are present. And when we targeted further to the left, we had from VISIR and LIPS a very clear, almost pure detection of akaganeite, so chlorinated iron hydroxide. So with very high iron content and presence of chlorine. And if you want to learn more, Erwin Duke has a poster today on this exact topic. So next slide, please. So to summarize this supercam view, in this unit, we see a fine-grained bedrock that is mostly composed of aluminum, potassium-rich phyllosilicates. But we also see some calcium sulfates, some fluoroapatites and fluorite, and strong enrichment in nickel. This bedrock is also enriched in ferric oxide, especially in the south, and it is cross-cut by sulfate veins and has concretions. And in the upper part of the stratigraphy, so we are seeing that the rocks are capped by a more massive iron-rich bedrock with at least some jarosite and akaganeite. Now, if we go to the next slide and start thinking about implications, the first thing to note is that well, apart from a very thin level of volume-enriched rocks, which Steph Connell will talk about in the end of this session. Apart from that, most of the rocks are relatively rich in silica and they are broadly lacking olivine. So this is a unique, quite unique lithology in the Jezero system, and which seems more akin to Gale crater, for example. A second observation is that its composition is relatively stable within the stratigraphy, and the variability we see is related to leaching of mobile elements, to iron oxides, to the presence of fluoride, veins, concretions, and so on. And so we think that we see some extensive overprint of diagenesis and fluid circulation. And that possibly includes some hydrothermal processes, because we are seeing fluorite as well, which on Earth is more often associated with hot fluids. We also have indication of illite, so a typical mineral formed during burial and diagenesis. But here it's unclear if we are seeing processes that happened in situ or in the watershed instead. So finally, the upper part of the formation is associated with acaganite and jarosite, which record low pH and saline fluids, perhaps due to exhumation and oxidation of the bedrock. And so I'll finish here by saying that the Bright Angel Formation records a mosaic of diverse aqueous environment, of diverse fluid activity, potentially stemming from enhanced diagenesis and hydrothermal system. And so that offers a compelling record of Mars' past aqueous environment. And with that, I'll stop here. And I thank you for your attention.
Okay, next I'll introduce our moderator, Audrey Putnam. Do coarse-grained river sediments reflect the chemistry and mineralogy of their sources in a Mars analog watershed in Iceland? Sometimes.
Yeah, so we're going back to Earth and looking at how a specific case in a watershed on Earth might be able to help us understand how to look at variability in our sources and how that gets translated into generated sediment and sediment sorting. So I wanted to start off with this video. It's coming through a little bit grainy, but showing one of these mountains in our watershed region and then the river cutting into it. So we're going to be looking at both of these components and how one gets translated to the other in the sedimentary system. And I want to thank NASA for funding this work and then all of my collaborators on the NASA DigMars team, which helped make this possible. So let's start out with a hypothetical trend. Let's say we see a certain correlation of data on Mars. Often we have multiple hypotheses for explaining a trend that could potentially fit for one particular oxide or set of oxides. For example, we could try to explain this particular trend as sorting of plagioclase phenocrysts from a more mafic ground mass, from a diversity of igneous compositions that are being accessed at different parts in the evolution of a watershed, and or the weathering of fine sediment. An assumption that is often used to try to resolve these uncertainties is assuming that the coarse fluvial sand and gravel represent the chemistry and the mineralogy of the source rocks. However, we know this is not the case in a lot of watersheds on Earth. And we know that generated sediment and the subsequent sorting of that sediment are ultimately determined by the textures present in the watershed, and that this requires first-order rock type specific studies in order to figure out what the different phases are and then how they're contributed into the sediment. So here we want to ask, does this coarse river sediment and gravel, does its mineralogy and chemistry actually match the rocks in our source region? We do this in a watershed in Iceland at Lake Sandvat, where we have a small first-order catchment with a basaltic, cold, and young landscape where we can extensively sample the lithologies and textures in our watershed and then the sediments as they come down from here. So we are mostly going to be focusing today on the sediments in that far river. So looking at the rocks above them and then the sediments down this river and into the delta. And then we characterize the mineralogy, the chemistry, and the microtexture of these. Okay, so let's start off with some of the interesting characteristics of these rocks here. So one thing we don't have here is large phenocrysts, which are often thought to be driving mineral-dependent sorting on Earth and on Mars. So from that perspective, this is a place where we should not expect to see significant mineral sorting trends. Instead, what we have is widespread quenching and brecciation of rocks erupted in lava-water interaction and widespread hydrothermal interaction, widespread hydrothermal alteration of basaltic glass into plagonite. And these watershed lithologies are really exciting because they also are a record of eruptive conditions during the formation of these rocks. So we have published last fall on the volcanic paleo ice record of this locality. And these are rocks that have been interpreted in various places on Mars from spectral analog and from geomorphology, and they may be telling us about past environments and ice on Mars's surface. So in order to understand the trends in the sediment, let's look at the textures of these rocks a little bit more closely. So I'm going to be stepping from outcrop scale down to SEM scale through a number of images. So here's one of these outcrops. We can see there's a lot of stuff going on. When we zoom in further, we can see that they're largely composed of two populations of clasts. We've got these larger, slowly cooled basalt, these black to gray clasts, and these are in a matrix of finer grained orange to tan quenched basaltic glass. Let's zoom in a little bit further. Let's take a look at this thin section in the center. We can see that we've got representatives of both of those populations of clasts. We've got a large black, slowly cooled clast in the center, and then it's surrounded by smaller clasts of quenched tan glass with orange alteration products filling up the middles. And we're going to step a little bit further through these two electron backscatter images from those representative types of clasts in this rock and look at the textures. And here I am just making them the exact same scale. That's 100 microns. So both of these are ultimately coming from the same lava. They're ultimately coming from the same magma chamber. So we would expect that they would have the same microphenocrysts. And that's what we find. We see that both of these have plagioclase and olivine microphenocrysts. The interesting and fun differences is what happens with the remaining melt when these lavas reach the surface. So in this slowly cooled clast on the left, we can see that the remaining melt was allowed to slowly cool into plagioclase microlights and then these nice dendritic clinopyroxenes. Whereas in the quickly quenched clast on the right, the remaining melt was quenched into volcanic glass, some of which has been hydrothermally altered into plagonite. And then we see these trends in the mineralogy expressed in the bulk XRD of the lithologies in the watershed. So here I'm showing clinopyroxene versus X-ray amorphous for a number of samples in this watershed. And we can see that there is a large variation in the crystallinity of these rocks between 0 and 80 weight % amorphous. And this trend also holds if we compare any one of these crystalline phases to the normalized sum of crystalline components, taking out the X-ray amorphous component. So this is not just autocorrelation. And we can also see that in this case, clinopyroxene is very well correlated with the crystallinity of the rocks in our watershed. And that's because for this particular volcanic system, you only form CPX when you allow that remaining melt to slowly cool. And this gives us a cool tool to look at quenching rate in our watershed and how that is translated into downstream sediment. So now let's overlay some of our, okay, here we go. Now let's overlay some of our sediment samples taken from, again, the coarse-grained river sediments in that river and delta. And what we can see, those are the open circles, by the way. What we can see from those is that they follow this trend very nicely. We don't see any evidence for additional amorphous material being added to these particular sediments, and that makes sense here. We can also see that they are showing a large variation in the weight % of clinopyroxene that is telling us about overall crystallinity. So it's varying between about 20 to 35 weight % clinopyroxene. Let's see. And then when we look at the bulk chemistry, there are some trends, but they're not that great. This is the best correlation with X-ray amorphous content of any of the major oxides, and it would be a lot harder to try to figure out all the details that are going on here. So just trying to figure this out with bulk chemistry would be a lot more difficult. And that makes sense because these are the same compositions of lavas that are coming up and quenching in different environments. Okay. We also don't see evidence for that watershed hydrothermal alteration being expressed in these coarse-grained river sediments. So on the left, I'm showing aluminum over silica and then mafics over silica for all of our samples. Broadly, we can see there's the distribution between more felsic and more mafic components of our system. but we know from our EPMA data that plagonite, that hydrothermal alteration phase, pulls up towards higher aluminum over silica. And we can see that we have two watershed rocks, some of those really amorphous 70, 80 weight% X-ray amorphous rocks are getting pulled up by the hydrothermal alteration, but we don't see that expressed in any of our sediment samples. We can also see from the bulk XRD on the right that we don't see any of these river sediment samples showing those really amorphous compositions. And we are not capturing that space of the watershed lithologies with these. When we turn to trace elements, it gets a little bit more complicated, and we might be starting to see a little bit of evidence for that. So we do see, I'm showing here chondrite normalized proportion across rare earth elements. In gray, that is the range and mean of the watershed rocks. And then green, that is the range and mean of those river and sediment samples. And we have a lot more here than we have for the XRD. And we can see that overall, these the river sand samples are enriched in rare earth elements, and especially in the light rare earth elements. And this is potentially consistent with some amount of plagnitic alteration being preserved in this. So this is an example of something that we might not be able to differentiate with bulk XRF or XRD at rover scale on Mars. But if we returned rocks like this to Earth, we might be able to detect these signals with the variety of techniques that we can leverage in a lab. Okay, so from this, we've learned that eruptive conditions can lead to large variation in the crystallinity of watershed rocks and in generated sediment, that textural correlation can result in the apparent sorting of mineral phases that are smaller than the clast size, that purely ground mass phases of a particular volcanic system can be powerful tracers of provenance erupting cooling environment, that bulk geochemistry alone may not be enough to distinguish all the geologically meaningful variation in our watershed, and that coarse fluvial sediments may be missing geologically important aspects of watershed variation, like that hydrothermal alteration. I'd be happy to talk about what this might mean for your sedimentary system of interest. I'm looking for a postdoc next spring. Thank you.
Okay, if our speakers, our last four speakers will come up to the stage, and folks can come up to the microphones here. Make sure to introduce yourself and your affiliation before you ask your question.
Hi, Sarah Preston, UCLA. I have a question for Lucia. My understanding was that LIBS couldn't do sulfur very well, so I was wondering, is that still the case with SuperCam, or did they fix it? And if so, how are we sure that the calcium sulfates you observed don't have some other surprise anion going on?
So yes, with LIBS we have issues in general with light elements, and we can detect sulfur, but it has to be at a quite high percentage in the rock so that we can detect it. But we can see some emission line for sulfur, and that's what we saw. We cannot quantify it, but since we detect it when it's high, and that we detected it, we can say that it's quite high. And actually, where we detected it was probably in veins where there is pure sulfate in it. And we also have other evidence. We have the Visayar and the Raman that's telling us that yes, it's calcium sulfates.
James Haber, Smithsonian. I have a question for Audrey. Great talk. Was wondering about, he said, so the plagonite was not really found in these coarse river sediments. Where would it be? Is it, in fine grained stuff in the delta or basin? Any thoughts on that?
Yeah, that's a great question. We do have one of our collaborators, Mike Thorpe, on this project is looking at cores of the lake sediment. And hopefully we will be able to determine whether that plagonitic phase is present in those sediments or not. But that's not the only option. It's also possible this area has had a lot of aeolian erosion. in recent historical times. So it's possible that that material has also been lost from the overall watershed by wind erosion.
Thank you.
So Paul Niles, Johnson Space Center. I have a question about the mudstones. Your interpretation was favorite interpretation was a lake. Do you have any thoughts on loess deposits and whether or not those those are mudstones? They show not very much alteration, which these mudstones don't seem to show a lot of alteration. What are your thoughts on loess as a possibility for an Earth analog?
Well, it's the thing that got us going, especially looking for justification to making this aeolian in the first place. And there are certain criteria that you have to meet to call something aeolian. And that probably, we discussed this at noon, aeolian intervals in there. I mean, the rover was going up so fast there, basically, we didn't really stop anywhere to really go for the nuts and bolts of things. But what I primarily want to point out is that there's a number of observations that are not really kosher, as you call it, all aeolian, and we're going to keep developing that to address it from one angle of the spectrum, basically, that this could be mostly lacustre with some aeolian intercalations, and then it is up to the people that want to make it aeolian to prove us wrong. Because at the moment, also reference to aeolian in the literature, in the recently published papers, goes to 2 or 3 abstracts a couple of years back. Nobody has done the hard work to really show it.
Kaushik Mitra, University of Texas, San Antonio. My question is for Lucia. So when we are thinking about the diagenesis of the diagenetic fluid, so since academia can only be produced in like chloride-rich fluids and jarosite generally is like produced in a sulfate-rich fluids, are we looking at multiple diagenetic episodes? And what temperature fluids are we thinking about? If I probably missed it in your talk.
Thank you for the question. So the idea that there was some diagenesis processes happening is not coming from the Akaganite detection. It's more coming from, for example, the E-light detection. So we would have like burial and then probably potassium-rich fluid circulation, and that's how you can form E-light. The Akaganite is probably decorrelated from these events. Probably you would have like exhumation of the bedrock and then oxidative fluids with some salts in it, some chlorine in it, but probably different from the diagenesis episodes.
Are we looking? So, do you have any suggestions on what temperatures are we looking at for the E-light formation?
Not really, actually. That can be, to my knowledge, the temperature range for E-light is pretty broad. So I cannot answer that question for now.
That's okay. Thank you so much.
Hi, John Lima, Johnson Space Center. Question for Dr. Schreiber. You mentioned that there were gypsum pseudomorphs. Do you have any evidence that those might be indicative of, is there anything texturally about those crystals that might be indicative of a lacustrine origin? For example, could they be bottom nucleated gypsum with the vertical growth orientation or anything like that?
Well, I mean, our main argument is that the laminites that we see so commonly in that whole succession with diagenetic products concentrated along discrete lamina is something that's very difficult to do during diagenesis of a aeolian deposited succession. It is perfectly easy to do it in a lacustrine setting. And not finding sand grains, that's really troublesome, especially if you can't explain how they sort of have disappeared suddenly, but you have no evidence for that. And then finally, we see laminites in there that look like spitting images of laminites at the bottom of the succession in Mount Sharp that everybody agrees upon, without exception, to be lacustrine.
Thanks.
Hi, Thanos Tadaris here, Purdue University, and I've got a question for Audrey Putney. So I'm really interested if you looked at the degree of aqueous alteration of the fluvial clasts in such a cold climate, what that would look like. And did you detect that the clasts were more altered than their source outcrops? And if so, how fast did they weather?
Sorry, were you talking about the phenocrysts when you were saying that?
I was talking about like the clasts themselves.
Okay.
Did you see signs that they were like more aqueously altered than the outcrops uphill due to the water interactions?
Yeah, so this is a quite small system. We're only about 5 kilometers from those mountains when things are getting down to the delta. So they're not spending a whole ton of time in residence in the system before they get down there. We don't in the river sediment see a lot of evidence for additional alteration. That would be a possible interpretation maybe of some of those elevated light rare earth abundances, but we don't see in the XRD or in the bulk XRF. That may be a different story once you get into the lake and start sitting there at the bottom of the lake and start getting buried. We're only looking at superficial sediments there. That also might be a different story in different parts of the watershed. I wasn't able to share it today, but we've also been looking at some of the intermittent streams on the north shore of the lake, where that sediment has a lot longer residence on the landscape. And there are chemical differences there that could be either an addition of tephra from out of the watershed or potentially some sort of alteration. And we're still differentiating that in specific.
Thank you. Great talk, by the way.
My question is for Audrey. My name is Katya, Brown University, and I was wondering about the temperature range that you're working with and whether you have some insight of what would happen if it's warmer or colder.
Yeah, so in terms of temperatures, I think there's kind of 2 sets of temperatures that we should be thinking about here, right? So that plagonization process I'm talking about, we don't think it's happening progressively over time in a surface environment. This is a process that we know from similar volcanoes that are eruptive in historical times in Iceland, that level of alteration can happen within a few years in a syneruptive hydrothermal system. We think that's most consistent with the petrography of what we see in thin section and in outcrop and in the data. So we don't see evidence in our samples for that further alteration necessarily that we're confident in. In terms of the temperatures of the overall field site, I don't remember off the top of my head the exact range, but it's Iceland. We were there in the summer, and there are some days where it was in the 50s, some days where you had a lot of wind and it was a bit colder, some days where it kind of felt like t-shirt weather, but it never gets that hot there.
Yeah. Okay. Thank you.
Hi, Samantha Baker, Caltech. Audrey, sorry, another question for you. I'm so curious if you see any compositional effects on grain sediment transport itself, like once you get to the river system. So not just which grains like form the core sediments, but are there mineralogical differences that affect how the grains actually move through the river system? Which ones get transported, which ones get deposited where?
Yes, so in general, there are, right? In general, we would think about the size of the grain and then the density of the grain, right? So when we typically think of mineral dependent sorting, we're thinking of either sorting minerals by their density, which is a bit harder because typically a lot of these basaltic minerals aren't that different in density. But there are environments where you can do that really efficiently, like a beach. And we do think we see a little bit of density driven sorting of materials on one of the beaches of the lake far away from that delta. But the other main control is going to be the grain size and of the minerals, right? You're not going to form monomineralic sand of something that you only have smaller than sand grain size. But none of the minerals in these rocks are that big, and we're pretty sure that all of the clasts, at least in that sand to gravel size fraction, are lithics and polymineralic. So we don't think that you're not sorting a single mineral grain from another single grain. What we're observing is textural correlations of which clasts in the bedrock have minerals, and then grain size, like sizes of those clasts that are driven by the quenching fragmentation rather than mineral properties.
Thank
So
you.
I hope that helps.
My question's for Lucia online. Mike Thorpe from UMD NASA Goddard. Just thinking back to your A, C, and K diagram there, and it getting pulled towards kind of the illite trend line there. Is there any correlation with kind of the strength of your illite detection from SuperCam with potassium, and like, does that give you more confidence in it being illite?
You mean from the strength of the Visier bands of potential detection of illite?
Yeah, however that works, like, is it a deeper band or whatever gives you more confidence that it's illite there with the potassium content?
Yeah, it's actually slightly deeper, but it's not a lot. You know, the bands are not really strong. But it's slightly deeper. But is it really significant? Is another question.
Yeah, thanks.
Mackenzie Day, UCLA. I have a question for Jürgen. On one of your slides, you showed the stratigraphic column and then the interpretation of aeolian interfluvial by the team, and then your deep water interpretation. But that strat column had cross-bedding in it, cross-stratification. Do you see that?
Yes, this was a simplified thing. It was sort of to get people's attention. We have no qualms with assuming that there are aeolian deposited intervals in there. We just have a very big problem to make the entire thing aeolian because we see so many lacustrine things in there. That the only problem with that whole strat section is that there are parts of it that are completely covered by debris. You could hide something very easily, say lacustrine or aeolian. We see places that have cross stratification in it, but that cross stratification is not conclusively aeolian because that scale of cross stratification, that style of cross stratification, we could see in fluvial deposits just as well. Okay, and so we never drove up to one of those things and sampled the grain sizes. But I mean, the cross-bedded stuff in there could be explained as fluvial incursions into a lake. It could be aeolian, but without a really careful examination, like we, for example, were afforded at Parum or some places like this, it is really difficult to make a distinction. It's not that these are 10-meter tall crossbeds. It's usually on the order of a half a meter to a meter or something like this, with 4 sets that I see in the fluvial deposits all the time. So it's just, let's me put it this way. I was astounded when that aeolian thing evolved, how easily it is to interpret these things so quickly. And in my opinion, nobody has really done the heavy lifting to make the aeolian thing stick. And it's probably not possible.
That one. Lucy, I have a question for you. You had mentioned towards the end that types 1 through 3 had these like coatings on them. Were these the coatings that we were like hearing, I think, on Tuesday's afternoon talks, like that purple coating? Or is this something different?
I think these are different. That those were the coatings reported by ChemCam, I think, SuperCam, like in Jezero. But these are different. So, and they have a different composition than the things that they were talking about on Tuesday too. So, yeah, so there's 2 different types of material that seem to be coating the class within the Geddes-Bavis Ridge system in the deposit. There's the gray sort of the type 4 material that's kind of gray color and has somewhat elevated sulfur, doesn't show as high magnesium as the bedrock outside the channel, but it's coating all 3 of the different clasts. And then we have this type 5 material, which has actually high sulfur, no cations correlate well with it. There is some silica in there, so there's probably some silicates, probably a mixture of sulfates, and there could be a little bit of elemental sulfur in there as well. It depends. We can't tell how the cations are attributed to the silicates. So you can model any number of different ways in, how much sulfate have you got there versus maybe how much there might be a little bit of elemental sulfur in there too.
Steve FASU for Jürgen. Seems like the laminite character of these rocks is very critical for either story. So are there lamanites on Earth, lacustrine lamanites on Earth that lack clay minerals? And conversely, are there any bona fide aeolian lamanites on Earth? I mean, can you find these rocks on Earth in those
Of
with
course,
those
I mean,
features?
everything we do is based on Earth analogs, really. Okay, but you can find, of course, lacustrine lamanites without a single clay grain in it. There's places where that happens, and see, when we say mudstone or shale or whatever, it's a grain size definition. It has nothing to do with mineralogy. You can have mudstones without a single piece of clay in it, and you can have sandstone with quite a bit of clay in it if you want to, because stuff gets altered or gets infiltrated and so forth. But the thing is, we can find lamanites like we showed here on Mars and elsewhere in the Mount Sharp succession. We can find spitting images for this on Earth. Okay, and there we know how they formed.
No. All right, let's thank our speakers one last time. All right. Next up, we have Michael Phillips talking about plagioclase-rich crust on Mars revealed in REA Basin, May 5th.
Okay. Well, thanks everybody for coming out to this late afternoon Thursday talk. So I'll be talking about some plagioclase-rich crust that we're seeing at the Argyre Basin. So this is a global map of all of the discoveries that I could find of plagioclase spectral signatures and CRISM data. And so you can see from this map that they're relatively widespread across Mars, although they're concentrated mostly in a few locations. The largest exposures of them are in Valles Marineris, and that was mostly done by Cristina Viviano, and then some follow-up studies later on by Flahout. And then in 2022, we published a paper about these in Northern Hellas, and you can see that there's a significant concentration of them in the Northern Hellas region. And then I'll be talking today about all the dots that you're seeing around the Argyre Basin, which is here in the middle of this map. And so when we're talking about these plagioclase detections, we're looking for this absorption feature that's relatively broad and centered around 1250 nanometers. And typically in the outcrops I'll be talking about today at least, they're sort of light toned and they tend to exist in these uplifted massifs around these basins. And I don't have time to get into it in this talk, but if you want to know more about the details of these spectral features and why the lithologic interpretation is difficult, I'll be happy to field questions about that in the Q&A. But suffice it to say that there's almost as many interpretations for their lithology as there are papers published about them. And just a small sample set here, they've been interpreted as some intermediate silica or evolved crustal component. Not a super specific lithology, but it's about as far as you can go with some of these. They've also been interpreted as granitic. They've been interpreted in the past as anorthositic. And then I've also interpreted them as anorthositic and more specifically, potentially members of what looks like a layered mafic intrusion. And that was for Northern Hellas. And I'm interested in these ancient uplifted massifs, and Christina did a great job of talking about one reason why the pre-Noachian rocks are interesting, and another reason why they're interesting is because they tell us something about the primary crust formation on Mars. And Mars is a much better analog for the primary crust formation on Earth because it's in a more similar size regime for early dynamics in the mantle than something like the moon, which isn't really a great analog for early crust formation on Earth. And so a hypothesis that's been put forth, first I read about it was in Baratal et al. 2014, and then from InSight data is that the lower crust of Mars might be lower density. And so, of course, I want to investigate that further because we found all of these plagioclase-rich deposits around Hellas, but it was unclear whether or not that was just a local thing or if this is really widespread and observable across the southern crust of Mars. And so this is just a quick summary of what we found and published on in 2022. So we have all these spectrally feldspathic outcrops, again, that I interpreted as anorthositic, but they were also associated with olivine-rich spectral signatures and low calcium pyroxene-rich spectral signatures. And so now for the rest of this talk, I'll be focusing in on what we found around the Argyre Basin and the uplifted massifs there. So the way we went about doing this is we used CRISM mapping data. So there's a really nice new data set that came out just last year, the MRDR-V4s. A big thank you to Frank Silos for pushing those out and a lot of other folks at APL. And so we use this specific band parameter combination where we track the band depth at 1300 in the red channel, the reflectance peak at 1 micron in the green channel, and then the low calcium pyroxene index in the blue channel. So the reason for the red channel ought to be obvious because we're looking for this broad absorption feature centered around 1250 or 1300 nanometers. And then the RPeak1 helps us differentiate these from olivine because you can see this, the reflectance peak ought to be longer wavelength for plagioclase than for olivine, and so these will show up as yellow. And the reason we track low calcium pyroxene is to avoid fake news in our spectra, where if you put LCP in the denominator, it'll basically make a fake plagioclase spectrum, so you want to avoid that. So here's a summary of our results. We've mapped over 1,300 different outcrops around the Argyre Basin. And we're interested today in the primary mineralogy, although some alteration mineralogy was also mapped. And so this is just a quick overview of the distribution. You'll notice that there is a sparse amount of detections in the southern Argyre rim, and that's mostly because of this seasonal CO2 ice, making the data quality worse in the southern hemisphere. But in the northern, or not hemisphere, but the southern rim, and in the northern rim, we see a lot more detections. And then this is just a figure showing our average spectra for these different types of detections. One thing you can do with the distribution of these minerals is you can use the distance from the center of the basin as a proxy for the depth of excavation. And so we filtered out the units that were outside of these geological units, which I got from Domedal 2015. And these geological units contain uplifted material. So the spectral signatures we're looking at are in this uplifted material. And this is what their distribution looks like as a function of distance from the center. And so on the right, you see the counts normalized as a percentage of the geological unit. And so the numbers only go up to a few percent. And then I've normalized them here to 100% in each radial bin, just so you can see trends more easily. And so one interpretation for what we're seeing here is a transition from upper mantle and lower crust uplifted material and into upper crustal material. And we see a clear transition from the red, green, and purple, which are all olivine bearing, to that low calcium pyroxene bearing material. And interspersed throughout in this middling zone are the plagioclase detections. So they seem to span this lower crust to upper crust transition that was uplifted by the Argyre Basin. And here's what they look like in CTX data. So this is kind of a typical plagioclase-rich outcrop. You can see it's very light tone compared to its surroundings. And they're almost always on these massifs. And when they're not, they're in crater rims. And then here's a high-rise image zooming even further in. You can see the sort of massive texture that they have. And perhaps it's difficult to tell sometimes erosion from actual layering that exists within the uplifted massif block, but perhaps some layering. So here is a high-rise red channel where we don't have color coverage, but you can see the light-toned bands, which I interpret as the anorthositic material. There's some good spots over here where you can see sort of these dark tone bands going through. And there are many, many examples like this, but I don't have time to walk through them all. And if we compare it to a similar type of texture that we see in the Hellas mass east, where you can see this sort of same layering, and then here I'm comparing it to layered mafic intrusions that we see on Earth. And the spatial scales are somewhat similar, although I think the layering is perhaps a bit thicker in the Mars examples. Okay, so now we get into hypothetical land, which is where I prefer to live. So one way you can explain these outcrops that's consistent with my interpretation of them as layered mafic intrusions, perhaps, is in the wake of cumulant mantle overturn, you have a really unfathomable amount of melting occurring. And the composition of the melt is going to depend on where it came from. Did it come from the shallow portion of that overturn or the deep portion? In one scenario, you have alumina, and then in the shallow sourced material, you essentially have no alumina to speak of, so you couldn't form the plagioclase. And I'll just consider this degree 1 overturn event, which some have proposed could be the source of the dichotomy. But in a scenario where you have the degree 1 upwelling centered over the southern hemisphere, you would expect these deeply sourced melts to be centered over the southern hemisphere, and then these shallow sourced melts over the northern hemisphere. And so you could have a scenario where you have the primary crust forming from these voluminous melts, takes a long time to cool, it's sitting near that surface and settling into something that would look like a layered mafic intrusion. Of course, the talks after me are going to be perseverance, and we're seeing some of these leucocratic rocks that could be anorthositic. Jezero could have uplifted Isidis uplift. And I have some other things to say potentially about pyroxene in the mantle that we're seeing with these olivine plus HCP rocks, but ask me about that because I don't have time to talk about it. Okay, thank you.
Okay, next up we have Arya Udry presenting igneous compositions on the rim of Jezero crater using SuperCam data.
Thank you. So today we're going to switch back to Jezero crater and talk a little about perseverance and those really cool igneous composition mineralogy that we have observed in the crater rim. So just for maybe some of you don't really follow Mars 2020, so let's talk a little bit more about the previous campaign. So we first started on the crater floor. Is that my laser? Yes, on the crater floor when we found several types of igneous lithology. We then went to the fan where we found in the delta front and the upper fan campaigns a bunch of sedimentary rocks. We then went to the margin, you can see in green, where we found a bunch of different things that we don't really know what it is. And then we're now in the beautiful crater rim. So the crater rim is Noachian, possibly pre-Noachian in age. And with this, possibly it could tell us more about early magmatism on Mars. So let's zoom a little bit on the crater rim. You can see right here in Sol 1293, this is by St. Elmo Pass. This is where we started to see really those crater rim composition. And the question that I have that I'm interested in is that, did we find igneous rocks, igneous mineralogy in composition? So here today, we're going to focus on SuperCam data, especially the LIDS, laser-induced background spectroscopy, which can measure remotely targets from 1.5, 2 meters to 6.5 meters accurately. And then also a remote micro imager, pretty much really nice images. So what I want to mention too is we have collected I mentioned only 2, but now 3 samples from the crater rim, the first Noachian samples that we have collected, which is quite exciting. The first was Silver Mountain in Sol 1401, that is pyroxene rich, and then also Green Gardens in Sol 1423. This one is serpentine rich, possibly. So again, did we find igneous rocks? Did we find igneous composition? The first thing that we look at to know what kind of rocks we have is looking at textures. So we have found different igneous textures throughout the crater rim. I'll just put some examples right here.
with crest falls and ages 1294, you can see this like coarse grain, phaneritic texture with subhedral minerals. As you can see, I'll try to draw maybe some of this angle, those angular possibly boundary of those minerals. We have more fine grain textures. Again, some coarse grain textures you can hopefully see right here from the elephant target. And also some kind of weird texture that we found in Duran and Macaca. Targets are quite close to each other. They possibly could be igneous texture, but also possible breccia. Actually, Audrey Putnam kind of showed similar texture that was seen in Iceland, I believe. And this was talked about by Candice Bedford and also Brian Horgan on Monday afternoon. So again, a lot of different texture that appear quite igneous. Let's switch to the mineralogy. So what's really cool with the LIBS, it has a beam and a beam size that vary between 150 micron to 450 micron, depending on the distance to the target. And using stoichiometric data that you can see here in this table on the lower right, it's too tiny, it doesn't matter. This is really just a variable that we use to detect if we have in our beam analysis, our point analysis, one single pyroxene, olivine, and plagioclase. And what's really cool about this campaign is we found a ton of pyroxene. And by a ton, I mean exactly 91 pyroxene, which is a lot compared much more than what we found in the different campaigns. So hopefully you can see on the map in the upper right, those little orange square represent location where the pyroxene have been found. If you too far in the back, it's just pyroxene have been pretty much found everywhere in the crater rim. So what's really cool with them is that most of them are actually low calcium pyroxene. So you can look at this pyroxene quadrilateral on the left you have magnesium, on the right you have iron, on the top you have calcium. All the point down purple red represent the crater rim pyroxene, and you can see that they're all low calcium pyroxene. 89 of them actually OPX and pigeonite, where we'll have two sad little CPX up there. So they have, as you can see, low iron composition, high magnesium composition, which differs a lot from, for example, pyroxene that we found in the crater floor. So they're really primitive. And this was confirmed with the SuperCam Raman, the Vizier, and actually, as Alicia Vaughan is going to show us after, by Masscam Z. So again, very primitive, a lot of pyroxene. We found also a lot. Other igneous minerals, we found plagioclase, which is quite exciting because we think like throughout the whole traverse, it's been hard to find plagioclase probably because they're too fine grained. But we have found four of them just with, again, the LIBS technique. They all have this labradorite composition, which is quite typical for what was found in Jezero crater, and also typical to what you find in Martian meteorites. And they were found, you can see, hopefully this blue square right here close to Eagle Cliff. We also found some olivine, only 8 of them, which was quite surprising. It might be just because we might not have targeted the right targets, but we have found 8 olivine with forsterite between 74 and 76. It's relatively primitive. It's not extraordinarily primitive, but it is. And this is also, they represent composition that were also found throughout the whole traverse. What was also really cool is that we found some quartz, likely not igneous quartz because we didn't find other igneous minerals, but hydrothermal quartz. But Emons Glacier, this is the target you can see right here in Sol 1315, where it was found. You can see that yellow square right over there. Again, possibly representing hydrothermalism. I invite you to check out Pierre Beck et al. 2025 paper. That's really cool. Okay, so we have all those minerals, but what's also really cool is we have found the first pyroxenite encounter at the surface. We have found between 8 to 10 rocks from St. Elmo Pass, as you can see here in pink, to Shallow Bay, so 2 different points in the inner rim and outer rim, pretty much. They all contain low calcium pyroxene, all kind of have the same composition. And again, we have, as you can see, this crest fault target, kind of, again, this phaneritic coarse grain textures. And this texture and actually composition is quite similar to the pre-Noachian Martian meteorite, Allen Hills 84001, that is 4.1 billion years old. I'll show you this rock after. We also have found some potential gabbro with both pyroxene and plagioclase in it. As you can see in the blue points right there, at least 2 to 4 rocks. Again, all of them are low calcium pyroxene. with potentially similar composition of the basaltic class that we have found in the Martian meteorite, this polemic breccia called Northwest Africa 7034. So let's compare those rocks, those igneous rocks, to Martian meteorites. The only samples that we have from Mars are now on Earth. So if you look at the texture of Allen Hills 84001, again, this also pyroxenite that's 4.1 billion years old, it has the same pheneritic coarse grain texture that we have found in those pyroxenite, which is really cool. And this is just an example of a gabbroid class that was found in this polemic regolith breccia. And those classes are likely 4.1 billion years old, the oldest Martian rocks that we have here on Earth. We can also compare the pyroxene composition of the crater rim pyroxene you can see here in red with all the Martian meteorite composition. And you have in black the polemic regolith breccia pyroxene, and then hopefully you can see in orange here the Allen Hill 84001. And you can see that the crater rim composition is slightly more primitive. So regarding the mineralogy, again, the pyroxene crater rim, low calcium composition, very primitive. It's similar to superficial orbital observation when we have more low calcium pyroxene composition. And the more primitive also the pyroxene that were found in Gale crater and Gusev crater. The olivine is a little bit weird because they're more scarce. They're quite scarce. And actually, I didn't tell you, but the pre-Noachian meteorites, they actually are the only one that really don't have really olivine, maybe some late stage olivine, but almost nothing. So maybe that means that we had different condition in the pre-Noachian. Maybe we have higher oxygen fugacity that could have prevent olivine to form. So to conclude, we have found various textures and composition, including igneous in the crater rim. We have really primitive pyroxene and slightly primitive olivine composition. It's slightly more primitive than the margin campaign that were before. And we have similar mineralogy as the Noachian meteorite, the two Noachian meteorites that we have. And also, this also could represent impact processes, maybe breccia, shock metamorphism, and also hydrothermal activity. This is something to discuss more. And finally, again, we have really cool Noachian samples. This is the only one that we have. Let's bring them back. Thank you very much for your attention. All right, up next, we're going to have Alicia Vaughn talking about multispectral and textural variability in low calcium pyroxene bearing lithologies in the Jezero crater rim.
Great. Thank you. Haria's perfect lead-in for me. I appreciate that. I'm going to give you the MassChem-Z perspective on the really exciting and diverse low calcium pyroxene that we've been finding in the crater rim. So is this the, yes. So I'm sure by now you're familiar with MassChem-Z, but for the few that might not know, it is the stereoscopic and zoomable camera on Perseverance that makes use of a filter wheel so we can image between 400 and 1,000 nanometers, really sensitive to iron-bearing materials. I think that the significance has already been stated of the importance of kind of tracking low calcium pyroxene is associated with the ancient cratered terrain and with the oldest meteorites from Mars. So we're interested in finding it. Here are some examples from our MassChem-Z data set at Jezero crater. So that's pigeonite at the bottom. And just, you know, we see this nice broad 900 nanometer band. And the minimum position moves between 910 and 940. That's not consistent, but that's what it looks like. And just to show you that we can pretty easily differentiate LCP from olivine bearing examples that have a 1 micron band. That's what that looks like in our data set, and from ferric oxide materials that have the 528 nanometer band, and especially with hematite, a shorter wavelength of absorption just below 900. And then nicely, when we put this, use these wavelengths in our decorrelation stretch images, things that have a 900 nanometer band tend to show up as purple. Things that have a 1 micron band tend to show up as blue, which is a helpful guide for us as we go along. But I wanted to back up and give you a little context on where we have seen low calcium pyroxene before we got to the crater rim. So jumping into this box, that's our, of course, geologic map in the background, where we landed, the different units. And my triangles here are where the MassChem-Z instrument had significant detections of LCP before we got to the crater rim. So not much in the crater floor at all. When we got to the fan front, which is the laser here? Oh, yeah. All right. At the fan front, we saw LCP in float material, really, just loose cobbles and pebbles sitting on top of the Shenandoah Formation. But notably, the knobs member of the Shenandoah Formation did have low calcium pyroxene, but it was very ambiguous as to whether it was in place or not. It was one block that did not have the lateral continuity that the other units had, and it was kind of surrounded by regolith. So it was very hard to tell. And then when we were on the fan top, we saw in the boulder rich unit, so again, in float, LCP rich boulders on the fan top, and then also a handful of LCP rich clasts that were embedded within the Otis Peak coarse grained sandstone. So, and then when we dropped into Neretva Vallis, there was this intra-channel mound we called Mount Washburn that had a really diverse population of cobbles, float material that included the target Atoko Point, which I know is a favorite, and Michael showed it in his talk. So the point being, most of this stuff was in float material sporadically throughout Jezero Crater. Those are the spectral examples from our data set. So we've had the opportunity now to study these two places kind of in depth, the inner crater rim and then over the crest to the outer crater rim in this area of Witch Hazel Hill. And we've seen a whole lot of low calcium pyroxene. And it's really exciting because it's in a whole lot of different lithologies, not one type, which is what I want to show you today. So looking at the inner crater rim, that series of ridges that we were able to investigate, all these dots are places Mastcam Z detected. Low calcium pyroxene lines up nicely with what we've heard from SuperCam already, but they're not all the same. I just color coded them by kind of their lithologies here. So jumping in, this is this really dark toned, coarse grained, ridge forming, blocky unit that had the strongest low calcium pyroxene bands Mastcam Z has seen to date. This is what Aria was just calling a peroxenite in the SuperCam data. So that's one example that we saw at those purple locations. Then at the base of Curtis Ridge, we saw LCP mixed with this really oxidized flavor. Hopefully you can see how red these rocks are, even in, look at those pink rocks, even in our enhanced color. So these are telling us about the difference in oxidative weathering that might have happened to these low calcium pyroxene rocks. I don't have confidence that we saw these in place in Curtis Ridge, but there is a collection of them here at the bottom of Curtis Ridge. Then we got to Eagle Cliff. This is where we started seeing the feldspar dominated rocks, which was really exciting. This is what they look like, very different in outcrop, in texture, expressions from the ridges we saw before at St. Elmo's Pass and Curtis Ridge. So these were lighter toned, they had really shiny lusters and super rough surfaces. We couldn't actually find a place to put the proximity science instruments down to get an abrasion patch or study them with detail, which was disappointing because of the roughness of this outcrop. And I just want to show you this Mother Mountain target. Oh, there's spectra for those with our 900 nanometer band. Just an animated GIF, thank you Thanos, between the enhanced color and the right eye to show you the kind of small scale variability going on in these rocks. And we know that the purple tones here are what's giving us our 900 nanometer band, probably the low calcium pyroxene, but you can see it's a smaller component of these rocks that are really dominated by feldspar. And this is what that outcrop looks like. So hopefully you can get a sense for how rough it is. This rock was on the previous slide. So really different and interesting. Here's one where we were co-located with SuperCam. So you can see Mastcam Z enhanced color on the top and the right eye decorrelation stretch on the bottom. Again, showing you that kind of variability, and the RMI here giving you the close-up textural view just to highlight that kind of luster for you again. And here's the SuperCam LIBS data. This is a great example from their 5-point LIBS raster with really two populations. 3 of the spots are right here on top of the feldspar standards, and the other 2 are down here by the pyroxene standards. So pretty awesome. And you've heard a lot about that from other abstracts this week from Aria, Candice, and Kathy has a poster if you want to know more. And then we also saw low calcium pyroxene mixed with olivine. here at Mist Park. A different outcrop yet again. So hopefully you can see the different expression of this outcrop has like, you know, this kind of almost lobate looking expression is different from the blocky outcrops we saw at St. Elmo Pass and Curtis Ridge. But again, this is olivine dominated, but does have low calcium pyroxene in it, which we saw in abrasion patch and with other instruments. And the spectra seem to bear that out too. We don't have these nice 900 nanometer pyroxene bands. We don't have a nice 1 micron olivine slope. Instead, we get these shifted bands that, you know, vary between 940 and 980, which is consistent with a mixture of olivine and low calcium pyroxene. So then quickly over to Witch Hazel Hill, where we've been recently, we were able to abrade at South Arm into yet some more low calcium pyroxene bearing material. And then up here at Shallow Bay, which is really exciting because this is a potential mega breccia block that we were able to abrade and collect a sample from. And I put a big star because it's the biggest 900 nanometer band depths now we have to date. And some more float rocks at Millbrook area. Here are spectra for those. So the blue one is our best, strongest 900 nanometer band from the MassChem-Z data set. And then what those look like in outcrop form, just so you can see again, this variability. We're just kind of seeing LCP everywhere, which is awesome. I've outlined the potential mega breccia block at the top, and the little yellow block box is where our abrasion and sampling took place for the Blue Hill. And this, for the spectroscopists in the room, is the 939 band depth throughout the course of the mission for MassChem-Z. So you can see not much happening in the crater floor, in the fan front and fan top, where we saw the boulders and mostly float material, but you can see kind of the explosion in the crater rim and the strongest band depths to date. So just to update that map then that I started with to show this as we've gotten into the crater rim campaign, my updated triangles of all these detections of low calcium pyroxene, and then mostly now it's in situ instead of float, which is awesome, and we've been able to sample it. So it's common. It exists in a lot of different lithologies, which is exciting. It's obviously an indication of our transition into Noachian terrain. And some of this is going to inform what kind of alteration took place pre-Jezero. And these are potential source outcrops for the float that we saw in the LCP Ridge float within Jezero crater. That'll take a little bit more work to look at, but that's what I'll be doing next, and I'll leave it there. Thank you.
Okay, our final speaker is Steph Connell, abrasion dehydration experiment at Bright Angel Jezero crater using SuperCam onboard Perseverance.
All right, hello, my name is Stephanie Connell. Thank you for introducing me. I'm a PhD candidate at Purdue University. So yeah, today we're going to be talking about an actual experiment that we performed in Jezero crater using SuperCam. So just to provide some context, so we're really switching the topic here to water on Mars. So trying to understand the hydration state and the distribution of water-bearing minerals on Mars is very important for uncovering Martian geologic, hydrologic, and atmospheric evolution. So there are basically a variety of factors that can in fact affect the stability of these hydrous minerals on Mars. And we really know this because for the past 30 years, many scientists have been studying hydrous minerals in Mars chambers. And it was actually Bishop and Peters, 1995, that were the first to see the 1.9 micron H2O band change. That was attributed from the fact that the hydrous minerals were, put in under, current Martian surface conditions. And there was the, indication that dehydration was occurring. So what we can see here is that for the Mars chamber investigations, we have these different environmental controls that are used that are obviously on Mars. So that's anywhere from, UV radiation fluxes coupled with solar radiant heat, relative humidity and temperature, which can influence the stability of minerals. And here's just a quick plot, from some of the work that I did recently that showed that phyllosilicates can in fact begin to dehydrate within 24 hours of exposure to Mars surface conditions. So with that, I realized that SuperChem has the 1.9 micron band that is used to calculate whether the dehydration is occurring, and that Meta, Perseverance's environmental package, actually can record all of these environmental controls, relative humidity, temperature, pressure, etc. So we combine both of those to use to basically perform a dehydration experiment. Okay, so I'm going to briefly describe what we did with SuperChem using the Perseverance rover, my trusty lab mate. First off, we wanted to abrade into the subsurface of Jezero crater in an outcrop, and that's an abrasion patch. You can see, whoops, sorry. We're going to go back one. That's an abrasion patch that you can see right there. So that basically, exposes the fresh subsurface materials. And essentially what that does is it's like fresh materials that are then being exposed to the Martian atmosphere. So SuperChem typically waits about 44 plus hours before characterizing minerals in abrasion patches. But we know phyllosilicates and other minerals can begin to lose adsorbed water within 24 hours. So what we did was we kind of, arranged the plans that happened within the rover, and we did our very first measurement 22 minutes after abrasion instead of 44 hours. And we did that on the Steamboat Mountain abrasion patch. One extra thing just to note is that it's very important to, indicate the times of the abrasion in which those happened, because that can also influence the 1.9 micron band. So here is a Bright Angel where the actual experiment took place. This was covered just recently by Lucia Mandon. So she went into, more details about this. So I'll skip over this just a little bit, but as a reminder from a few talks ago, Bright Angel is in Vallis. We're going to be focusing on the north part of Bright Angel at the northern margin unit contact. And it's basically light toned lithologies. That's, fine grain mudstone to siltstone. So here's the actual outcrop that we did the experiment. So as you can see here, this is the Steamboat Mountain abrasion patch. We also have Apollo Temple and Walhalla Glades more towards the south that we're going to talk later on in the presentation. And essentially what we see here is that the Steamboat Mountain abrasion outcrop here at Beaver Falls is olivine bearing. It has an iron oxide red matrix and calcium sulfate. So that's, a weakly stratified granular conglomerate that's dark toned. And then actually beside it, we have the Chauvet Falls outcrop that actually, they're pretty like texturally and mineralogically distinct, because this outcrop here has like phyllosilicates, so luminosilicates, potentially illite, and then calcium sulfates as well, but both in the matrix and in the veins here. This is mostly anhydrite, but we actually see a mix of basanite and anhydrite in the Steamboat Mountain Glen Rapids member. So here's just the overall spectroscopy. So we can clearly see that there is a 1.9 band, 1.93 band for the SuperChem data. And we did these observations on soils 1191, 1192, 1193, skipped 1194 and went into 1195. But the overall mineralogy using the SuperChem techniques of the Raman and the Libs tell us that there is olivine present. We see that the reddish-brown matrix could be indicative of ferrohydrite. And in fact, this spectra does show that we see a spectral signature consistent with olivine mixed with ferrohydrite. In DeHook et al. 2017, they did some mineral mixtures for that. And it's not totally clear that there's sulfate here, but we'll talk about the Sherlock data and how we actually were able to constrain the hydration phase of the calcium sulfates. So we'll go next slide. So here's the actual band depth calculations. And as you can see, there's only 2 sols that I'm showing here. And that's really because the rover had some ARM activities in between the SuperChem activities that resulted in the IRS field of view shifting just a bit. And of course, it's also can be indicative of thermal expansion of the rover mass that SuperChem is then sitting on. But if you look from point 9 here and point 9 there, they look relatively the same. So we didn't really see any changes that are greater than 2% that are visually apparent in the 1.9 micron region here. And that, basically have that are like visually apparent that we can actually see with the eyes, but then the calculations do indicate that there isn't much of a difference. But SuperChem measures bulk hydration. So Sherlock is particularly important for constraining the hydration phase, which you can see the Sherlock DUV Raman there, where we're seeing an actual mixture of basanite and anhydrite, which is actually inconsistent within the Steamboat Mountain abrasion patch, where we see areas that are more hydrated than others. So with doing a, dehydration experiment in Jezero, I'll just show you where the Bright Angel location is. I wanted to know what the overall hydration state was of Jezero crater to sort of get a sense of what we were looking at here. And the 1.9 bands in general aren't as deep. So if we kind of dial back to the Apollo Temple and Walhalla Glades abrasion patches, which are in the Bright Angel region with Steamboat Mountain, we can actually see that these 3 abrasion patches average band depth intensities for the H2O band depth is actually similar to that to the hydration state of aqueously altered igneous materials that we have seen in the crater floor. So that would be for like C to N mass. Well, this is a sedimentary deposit. It's just not very hydrated. It's showing some of the lowest hydration that we've seen in Jezero crater. Looking at the SuperCam data, and this is also pretty consistent with the Sherlock data, we are seeing that the fan front and the fan top are showing some of the highest hydration. So like, close to 20 band depth percent. And then it's followed by the margin unit, which is like a mixture of olivine carbonate and other mineral assemblages. And of course, all along the Rover Traverse here, we do see that there's a mixture of magnesium and calcium sulfates that are of different hydration states, and of course, phyllosilicates. All right. So in order to sort of get a sense of the surface and atmospheric interactions that are happening on Mars, we then paired it and co-located it with META, which actually took some of, oh, sorry, I keep going back. So using the laser here, we have the temperatures for during the times of the experiment, the relative humidity, and the UV radiation fluxes. So we have the times here, we're looking at a range of -10 degrees Celsius to -32 degrees Celsius temperature when at the time of this abrasion dehydration experiment, also indicating that, this is done in the winter of Mars, so it was relatively cold. A lot of these Mars chamber experiments do happen at room temperature, which actually might motivate the fact that we see some of these changes happening to these hydrous minerals. But META also tells us that the relative humidity is effectively 0% at the time that these measurements are happening. And another interesting thing that we discovered by comparing the atmospheric data to the SuperCam data, and based on the times that we actually do these measurements on Mars, is that we do it during the time where the temperature is highest, the UV radiation fluxes are high, so we can see it's 32 watts per meter squared for this time on Mars during the experiment, and that we're doing it during the time that it's the lowest relative humidity. And this range here is actually the range of when SuperChem actually performs its experiments on Mars. So to conclude, Steamboat Mountain, the 1.93 band appeared to be relatively stable because we didn't see any significant changes. Again, we're looking for changes that would be greater than 2% because that's what we go for in the lab. And that's also changes that would be above the instrument noise level. We likely observed structural water and not absorbed water. So in the laboratory, we can see adsorbed water begin to liberate from the samples after 10 minutes. But we didn't see any, changes to the right long wavelength wing of the 1.9 band that would be indicative of that. These minerals are also not the type to have loosely bound interlayer water. So phyllosilicates like smectites, for instance, nautronite, hectorite, and montmorillonite would be probably better candidates for this because it has that loosely bound adsorbed water interlayer. So those just would, dehydrate faster based on their mineral structure. And it's really the minerals and their structures that will motivate the rate of dehydration that we see. Bright Angel is relatively low hydration in comparison to the rest of Jezero crater. And we're going to try to do this experiment again, but with, magnesium, iron, smectite materials, potentially in the Waukene basement, I think would be a pretty good candidate. And then making some modifications to the experiment to sort of avoid any sort of shifting of the measurements. And thank you so much. Looking forward to your questions.
Okay, so the last 4 speakers can just head on up to the stage and grab a mic. Go ahead.
Adam Valentinos, Brown University. Question to the last speaker. About this iron oxide matrix. So first of all, super exciting that you're identifying ferrihydrite, because we know that ferrihydrite is also in the global dust and it's spread everywhere. So my question is, just curious, how did you end up with this identification? Is it just based on the 1.9 hydration band, or is it based on something else? Because we know that hydroxides, a lot of iron hydroxides have the 1.9 band, which is quite just general identification of just chemically bound water. So
Yeah, so this is basically inferred from a combination of techniques, and I should have said Pixel also is inferring ferrihydrite within the reddish-brown matrix, and also they indicated that the reddish-brown matrix was amorphous, which would be consistent with ferrihydrite. Again, it could be associated with other hydrated minerals, and we do know that there's quite the mixture there. You probably saw the heterogeneity within the Steamboat Mountain abrasion patch. Also, the 2.31 micron band is extremely weak, and that could be associated with other phyllosilicates.
Thanks.
Thanks.
Livio Tornabene, University of Western Ontario. For the first three speakers, so we know that basins can form voluminous melt, and that melt can differentiate and create igneous textures. The Sudbury impact structure has norite, gabbro, and granophyre, which is ostensibly an orthosite, just different because the target was different. So I'm just wondering if you're considering differentiated impact melt as a possible hypothesis for how these rocks came to be.
Yeah, it's on. Can you hear me? Yes, I think, and Bryony presented about that in the Jezero session on Monday. I think the impactite hypothesis, the two-layer impactite that you spoke about too, right? And the possible melt pond, I guess, on the ledge. This is definitely outside of my expertise, but other people on the team, I think, are certainly thinking about that.
I can mention it. And we talked about that like offline, but maybe not impactite, maybe not for the Jezero crater, maybe for the Isidis crater, as it was just much larger,
so-
because if we have also pyroxenite, we need like a thick impact
not
melt.
Jezero. Jezero would not have.
Okay, yeah.
I want to make that clear in this room. Jezero would not have a differentiated impact melt sheet. It is not large enough. So it would be Isidis, it could be Utopia, it could be Borealis.
Yeah. Why not? We need to bring them back and check the PGA.
Yeah.
And for the Argyre perspective, it's hard for me to imagine like the context in which we find these rocks in the uplifted massifs. That seems to be material that was uplifted by Argyre. So we would need to do like a more higher spatial resolution, detailed assessment of what these look like. But it seems easier for me to imagine that this was material that existed before the Argyre impact.
I would normally agree with that, but there are older basins that Argyre is into. So
Oh, sure. Yeah. If it was an impact melt sheet that happened before Argyre that Argyre impacted into is totally plausible interpretation.
And we're going to work together on that. So
I hope so.
Carl Allen, JSC, retired. Comment and a question. Comment is that doing hydration experiments on Mars is just elegant, and I think that is a wonderful piece of work. Question concerning the correlation between the two Noachian Mars meteorites, the only two Noachian Mars meteorites that we have, and the some of the data that you get from the rim, that suggests that Noachian stuff all over Mars might have some commonality, and seems like there's a dissertation in there to see how far you can push that particular idea. Comments?
Thank you. I think that sounds great, but I'd love to talk to you after for some more information about that. Yeah, almost done my dissertation, but looking for future postdoc projects, which I will be applying this year, hopefully finding a job next year. Just thought I'd put that out there.
to answer the meteorite comment, I mean, yes, possibly. I mean, we likely have, this proves again that low calcium pyroxene is likely much more common in the Noachian and pre-Noachian than it is later in the Amazonian. But again, we only have 2 rocks from the Noachian, so it's hard to mention, to know that those data are statistically significant. But this is what we see now. So again, we just need more samples.
Yeah, Roger Weens, Purdue University, for our first speaker. So my understanding is that the observation of plagioclase by this near infrared hinges on the incorporation of a small amount of iron in their structure. I'm wondering, I mean, there could be a huge amount of plagioclase on the surface of Mars, and we're just not seeing it with infrared, and we're only seeing the parts that have this little bit of iron. Can you say anything about what conditions would lead to the incorporation of some iron that would allow us to be seeing this? Are we seeing a really biased sample in some way because of that?
Yeah, absolutely. And that's a great point. And what's interesting is you can actually use the fact that you need to have a small amount of iron, and it truly is a small amount of iron. It doesn't take much. It's like tenths of weights percent. But you can actually use the fact that you're seeing this in the plagioclase to perhaps say something about the composition of the melt that formed it. So I have supplementary material in my 2022 paper that I'm trying to recall, but there are conditions that are preferable for this inclusion of iron, and it has to do with temperature and oxygen fugacity and cooling rates in some combination. Yeah, but I would point you to that supplementary material. I really go into a lot of detail into the iron substitution mechanism, which is a messy literature, and also the ideal melt conditions for this inclusion into the plagioclase.
Brad Sutter, Momentum, NASA Johnson Space Center. Question for the last speaker. Are you able to quantify how much water that those 1.9 bands represent in those samples?
No, we weren't able to do that. So the one way, I guess, to be able to quantify water on Mars would be the hydrogen with the libs, but we currently can't do that with SuperCam.
Okay. Is there can you do any type of calibrations with samples to, lab samples to try to take a crack at that in the future? Or?
Yeah, actually. So I was thinking about doing some follow-up laboratory studies. Number one, looking at ferrohydrite instability at -10 degrees Celsius, and also doing some mixtures.
Yeah.
And then maybe trying to quantify it that way. So I think what I would like to do is try to reproduce what we did on Mars back on Earth as a reverse sort of mechanism thing to see if it can provide any additional answers, and quantifying it would be very helpful. I agree.
Yeah, it'd be really cool because then you could compare that with the SAM data from Gale Crater, where we are able to quantify the amount of water that's in all the samples.
Yeah, exactly.
So it'd be kind of cool. All right.
Yeah, thank you.
Hi, I think this is mostly going to go to Aria back behind the pillar there, but I'm going to compare speakers 2 and 3 just a tiny bit here. So, Aria, you showed that wonderful cloud of pyroxene plots and pyroxene compositions from SuperCam. Then speaker 3 showed that there was pyroxene in at least 3 different lithologies, one with plagioclase, one with olivine, and one that was LCP dominated. Was there any difference in the composition of the pyroxenes between those 3 outcrops? And then while I'm at it, she showed that one pyroxene and plagioclase rich rock. Was that rock where you got all of the plagioclase detections that you showed, or were there other plagioclases somewhere in that traverse?
The answer to that. There was another plagioclase detection, at least actually in combination with the oxidized ones that I showed. Boundary Peak, yes, the SuperCam person, I'm pretty sure. Boundary Peak also had feldspar in it, which we can't see with Mastcam Z, and we didn't have the LCP in the exact same place they made the measurement, so I just didn't want to put that in my talk. But yes, plagioclase, but those were float rocks. So Eagle Ridge, I get the names messed up. That outcrop is the one that is in situ feldspar rich mixture.
Yeah, and for SuperCam, the feldspar we found was in edges, so
floats, unfortunately, but this is we're also limited with size. But yeah, I only saw LCP, I mean, also pyroxene and pigeonite by themselves, and then what I called gabbro, which was like 2 to 4 rocks, which have the pyroxene composition, I guess, was like slightly more calcium rich, like wollastonite 14 to 17, compared to the others, which was like wollastonite 1 to 5, especially for the pyroxenite. So the gabbro, that what I call the gabbro, which I just saw as pyroxene and feldspar, were slightly less primitive, more calcium rich.
And were they all clustered together along the MG axis also, or they just kind of a cloud the whole way?
Well, you remember this
Yeah.
trend that was like this, and then the pyroxenite are here and the gabbro there, but we're going to do some more modeling on that.
Hi, while you're up there, Adrian Brown, Plantis Research. So you mentioned in your talk about the controls on olivine, possibly being related to fugacity. Yeah, how would that work? Any thoughts or?
I don't know. I mean, what was mentioned for Black Beauty, the polemic regular spreadsheet, there's no olivine in it. The only olivine that it's in it is in disequilibrium, formed through shock. And it was mentioned that, a way to prevent this formation was oxygen fugacity. So probably maybe a more oxidized environment within the magma, maybe more water. I don't know.
You need the iron 2+, and if you don't have it available.
But it could
Well,
mixture.
but we still find it. You still have iron 2+, though. What do you mean? I don't know. When you
Yeah. What was the paper that was about Black Beauty that you were talking about there?
Santos et al. 2015. They mention it briefly, but yeah.
Yeah, because it is a big mystery why we'd see olivine, halfway through the history of Mars.
Again, we might just look at a subset of rock that's just very similar in the crater rim and the meteorites that we have. It's quite a coincidence. But we mentioned like you found olivine, Noachian, the pre-Noachian, Christina mentioned olivine as well. So it's like,
yeah,
we need just more rocks.
Indeed. Thanks.
Ellie Moreland, Rice University. For the first speaker, if you could share a little bit about pyroxenes that you don't have time to talk about, I would love to hear about it.
Oh yeah, for sure. So we found 2 populations of pyroxene bearing stuff. What I think is the most interesting is the olivine plus high calcium pyroxene mixtures, and they're closer to the center of the basin, stratigraphically lower, and I think there's mantle material uplifted by argyre, and this could be partially at least representative of some of that, which actually dovetails with a talk Alan Trayman gave yesterday, I think. So that's interesting, and I think we need to do some impact modeling to see and really constrain the depth of origin and get some probability assessments of whether or not we're seeing mantle material. Yeah, so it perhaps is unexpected given the literature history, but in theory, it just seems like it makes sense that there could be pyroxene mixed in there. And then secondly, we have the LCP population, which is probably this upper crustal, early secondary kind of crust, pre-argyre crust. Yeah, so those are the two pyroxenes we're seeing. And another comment about the HCP mixed in with the olivine, it could be that in some cases, perhaps what we're seeing is actually a spinel band of one form or another. So I'm calling it olivine plus HCP, but if you look at spectra of olivine mixed with chromatite, for example, from lunar rocks, it's a decent spectral match. Yeah, so it's interesting. Need to untangle that more.
All right, if there's not any other questions, let's thank our speakers one last time. And then just as a reminder, the poster session tonight will have a lot more of this Martian geochemistry. And if any of you want to be Dwornik judges for any of those, please come see us. If not, we'll see you at the poster session.
And just a thank you to our VFairs and our technicians over here that helped us out with presentation. Thanks.